I think I would pass the word to Jaqueline Godoy. And Jaqueline is a PhD fellow at our department at Aalborg University. She holds a Master of Science in Communication and a Bachelor of Engineering in Environmental Engineering, and her research focus on investigating the nested energy cultures of energy expert actors and their perception of the environment, the select products and the processes they undertake when driving social, technical, sustainable energy transitions. So I will leave the floor to you, Jaqueline.
Yes, thank you for the presentation and the amazing introduction. He did much better than me. So I'm kind of summarizing my thesis, and I'm wrapping everything together. So the name of my thesis is Actor Narratives for Sustainable Energy Transitions. So when we think about actors, then we need to see that in sustainable energy transitions there are some dichotomies. Some people think, oh, actors is all about institutions, so the institutions, the actors are embedded in the institutions, and so the actors doesn't have any decision-making power. And then there's other group of people that think that, yes, the actors have agency at a micro level. And what is important to consider in that the agency is a relationship. So even that maybe the influence is little, you have, when you think or when you produce something, you have some kind of influence into the system. So is this the instance that I'm adopting? My thesis is divided in two parts. The first part, I'm looking at agency at different actors, and the second part, I'm looking at social technical systems, how the different actors are behaving under social technical systems. So using the middle-out perspective, there's like different categories of actors. And I'm looking at middle actors that are facility managers, project coordinators, small and medium enterprises, and researchers. At a top-down level, you can have like government that will influence society through regulations and funding. At bottom-up, you can have like a civil society and energy consumers that generally in those kind of sustainable energy transitions, they look at participation. How can they accept the system that we are proposing? So I think that the middle actors, they are enablers of the transition, and they have a strategic position in the network. They can enable action in action, and they can also change and stagnate the system. So they play a really important role when it comes to energy transitions. My research questions, I'm focused on the role of the perceptions that these actors have in relation to the environment, to the products, and to the process. And on it, I'm looking at the new theoretical narratives that are necessary to make the transition. And the new methods that are emerging, or the new technologies that are coming out of these interactions that the actors are proposing. And of course, some ethical perspectives, like for instance, questions of fairness, trust, moral, and power relation. In regard to new theoretical perspectives, I'm using this post-humanism perspective that is decentering the focus on the humans and open a little bit, considering that nature, for instance, is also an actor that enjoys its own agency. These scholars like Bruno Latour that I did a book review, and what's interesting to think about it is that it changed the way that we see climate change. Because if you think that the nature is responding to our influence on the earth, then they also have a role on it as a huge role. And so the nature is able to react to society rather than being the mere background where societal development happens. And this allows us to go beyond the dichotomies between local, global, globalize and localize, ecologize, and left and right. And this facilitates the communication, because people, at the moment that we understand that we are in the same level and the same standpoint, and all of us need to solve the climate change in order to move on, and need nature in order to survive, then we can really talk and be on the same page. So it changed a little bit the way that we think, and that the way that we are going to approach collaboration, interdisciplinary work, and those kinds of things in energy transition. So I see that energy transition is an opportunity to do not perpetuate the inequalities of the current system. So if we change the way that we are thinking, we can not just maintain the status quo where you have like a lot of powerful actors taking the decisions, and just society as a society. So in relation to the perceptions of the environment, those are two articles that are coming out. The first one is where I stayed 3 months in a Norwegian company, and I checked how the company is dealing with making innovation for the community that they are serving. So I'm also looking at what kind of influence they take out from the external, and also that they implement in their daily life and in the process that they are undertaking. So it's complicated to understand how the behavior shapes people behavior, because the environment is a relative term that changes depending on the people and changes over time. So in order to see what's necessary to be done in the energy transition, we need to detach from human beings' style of living. Then you can take a zoom out perspective and really start to propose some things that will accelerate the transition and have a more common ground for it. The second the second article that's coming out is related to the artifacts. So the artifacts, they are transformation of the raw material. And so when you are transforming or proposing something, making some innovation, you are materializing your thoughts. And those objects have some moral agency. So depending on your ethics and the way that you see society, you will be able to propose something that is aligned with those thoughts, those ideas that we have for society. So it's important to check, and I checked with 3 different companies what are their moral values. Then this is related to the second part of the thesis, that is institutions. So when it comes to institutions, we'll look at together with my colleague that she will explain this article in more details. How is the institutional configurations related to district heating in Sweden and Denmark? And then there is a really important point in relation to the Scandinavian culture that is trust. And people really will engage with socio-technical systems if they feel that their rights are respected. So it's important to think at a North Sea level perspective. It's important to consider that every country, every community will have different priorities and different things that is necessary to be looked at from a cultural perspective. So in the context of Scandinavian, it's trust. So in order to have fair institutional conditions and have a good district heating, you need to have fairness, transparency, and open dialogue. And this is important because district heatings are natural monopolies. So once you are connected to the district heating, you are susceptible to the prices that can increase quite a lot, like is happening now in UK, that the gas price is going up. So people will be maybe in full poverty. And this is a serious thing that's happening. And also recently there is some declining political trust. So it's been starting to talk about a post-trust era. So what's going to happen now that those societies doesn't believe more in the politicians? Then also related to socio-technical systems, there is a huge part of the energy transition that's called digitalization, because we need to deal with the intermittence of the renewable energy systems. And in this regard, I look at what kind of threats does it have? And then, I don't know if you know Susanna Zuboff, but she's a scholar that coined this term surveillance capitalism. If you don't know the term, I'm sure that if you have Facebook or if you have a phone, you have been receiving advertisements or things like that, and this is some of the influences and of the behavior of surplus. So you are being monitored, and then you are receiving some advertisements for third-party companies, and this has a huge of consequences like anxiety, depression, and have private issues and security issues. And then following from this book review, I was curious what's going on in the energy sector. So it's possible that now that we have smart meters installed in our house, that we are going to have some products being offered to us just because we wake up at a certain hour and we drink coffee. Then we can trace our electricity consumption and takes out some conclusions, and then the companies will start to go into this bubble of Google bubble that's everything is about advertisements and selling products back to the consumers. And then I check it in this article if this is possible to happen. And from a technical perspective, it's possible to happen. So we need a lot of regulations that are based in justice, political justice like John law, or things like that, that combined with the GDPR can give to the actors some perspectives of what can be done in relation to the digitalization and the many problems related to that. Just some preliminary thesis conclusions. So the narratives that consider moral values, ethical principles, and go beyond the dichotomies are really relevant and important, that we start to think a little bit more in a flat perspective. Also, I will say that this is of responsibility of the middle out actors that I was looking at, to act in an ethical way, preserving the values and norms of the community in which the system is inserted, to be open to community innovations. It's called technological possibilism instead of technological determinism. So look at what the society is asking for and just see what can be done. And implementing a new business model like ownership models that the community can be more participant on the decisions. And distribute power of the decisions concerning the future of energy systems. And related to the data, the actors who hold citizen data and create behavior models must act in accordance with the GDPR. Also, it's necessary to have a framework more adequate for the digitalization of the energy sector that prevents the practice of surveillance capitalism. Yeah, thank you.
Which is Jinxi Zhang. She's a PhD candidate at the Chalmers University of Technology with a master in integrated climate science from the University of Hamburg, and also has a bachelor in meteorology. Her expertise and research interests include agent-based modeling, electricity system transition, and energy system modeling. And previously, she was also a research assistant at the National Center for Climate Change Strategy and International Cooperation in China. So the floor is yours, Jinxi.
Thank you very much, Matt, for the introduction. So I will move back to the energy system modeling part from Jaqueline's philosophy area. So today I will give a brief presentation about my work together with my supervisors during the last 3 years during the ENSYSTRA project. And today my presentation is about transition to a low carbon technology system, an agent-based model approach of modeling investment decisions. So first, I want to give a brief information about this study. The overall aim of this study is to look at the transition of the energy, of the electricity system. And the tool we use for this study is similar to the ESRs present in the morning in work package 1. That is a computational model. But the differences here is that instead of use optimization model, we use the agent-based model approach, where we focus more on the heterogeneity and the limited foresight of the agents, as well as the uncertainties that agents have when they make decisions. And the model we have developed and used is called, we call it HAPPY. It's heterogeneous agent-based power plant investment model. And with this model, we focused on simulating the investment decisions from power companies. And during the last 2-3 years of our work, I think the overall and the direction of this work has been more focused on model development. So we focus on how we can build up an agent-based model to simulate our company's investment decision, rather than directly tackle the question that how to achieve a particular mitigation scenarios. So today's presentation will also be more focused on model development aspect. And I want to give 2 examples of the research questions that we have been studied. The first example is we look at how different hurdle rates that company use and how their different expectations for future carbon price have impact of their investment decisions, and how their decisions will in turn impact the transition of the energy system. So just a brief explanation about hurdle rate. Hurdle rate is the investment return that a company is expected. So if, for example, if a company use investment hurdle rates of 8%, it means that they expect one investment need to have 8% at least the return. Otherwise, they will not invest. And the expectation about future carbon price is that in our model, we implement a growing tax scenario, and different companies expect different growth rate. And this means some company will overestimate, some company will underestimate, and some company will relatively have a good estimation about the future carbon price. Yes, so one example of the results we have here is about the development of the installed capacity over 80 years. So here we show 3 different cases. On the left side, the first case, where we have homogeneous agents, which means a company here and they all use same hurdle rate, 8%, and they have the same expectations about future carbon price. And in the second case, in the middle one, company have the same expectations about future carbon price, but they use very different hurdle rate values. And in the third case, company use the same hurdle rate value, but they expect different carbon price in the future. And if we compare these 3 cases, one difference we can see is that in the later 2 cases with homogeneous agents, we see that the light blue and dark blue, which are wind and nuclear, they start to expand earlier. And the differences between those later 2 cases is that we can see that in the end, we have more wind, less wind, less gas, but more nuclear compared to this case. The brief explanation is because how low hurdle rate in this case have different impact on the levelized cost of different technology. So impact them differently. Yes. Okay. So a second example of the research question we have investigated is about the financing of the investment. So why we want to study the financing part? It's because in many energy models, financing is never an issue, because as long as it's optimized to invest, they just assume that the investment will be made. But however, in reality, financing can be an issue because the power plant is capital intense and the payback time is relatively long. Therefore, we have an explicit financial module in our model, and where we keep track of each company's financial status. And with this financial module, we investigate, for example, how do different levels of financial constraint and access to capital impact a company's investment decision, and how do they perform differently in terms of their economic outcome, and how does agents' decision and their performances in turn impact the pace of the transition. One example is shown by this graph, where we investigate the bankruptcy of different companies when we assume different parameter. The parameter we test here is the fraction that has to be paid by a company when they want to make a new investment. So for example, if a wind power plant costs 1 million and we assume F equals to 30%, this means that 30% of this 1 million has to be financed by the company itself, so from their own capitals. And what we can see from the graph here, and the x-axis is the F value from 0% to 50%, and the y-axis is the bankruptcy frequency. And left figure, we grouped different companies by the hurdle rate value they use. And the observation here is that in general, we see that companies use a lower hurdle rate value, more likely to go bankrupt. And then if we look at the right side figure, it's a same group of agents or company, but we group them by how their expectation about future carbon price. And the conclusion here is, or observation here is that if a company expects too low or too high carbon price, which is represented by the B value equal to 0 and to 2 here in this study, they are more likely to go bankrupt. And another figure I want to show here is that if we look at the system level, when we look at how emission reduction trajectory looks like when we assume different F value, and just remind you again, F value represents the fraction of an investment that has to be paid by a company's own capital. And here we observe that when F value is low, the transition is the reduction you see is faster, which we can say that the emission is mitigated more rapidly when the company is less financial constrained and have more access to capital. Yes, so I want to summarize by some key contributions that I think this study so far has been made. I think this contribution can be twofold. The first is a contribution to a development of model method. As I briefly described, we developed this agent-based model focused on simulating companies' investment decision. And we explicitly have a financial module that keeps track of companies' performances. And we also test different parameter assumptions, for example, the hurdle rate value and the carbon expectation and financial parameters, which are not always fully tested when we run a model. And the second contribution can be categorized as the better understanding of the transition pathway, and where we explored the transition and we focused on the heterogeneity, uncertainty, and financial feedbacks of the agents, and we look at how the decision could be hamper or enhance the transition. And we also illustrate some possible way accelerate the transition. For example, we see that low hurdle rate and high expectation of carbon price in the model have a fast emission reduction, and this means low risk and a clear carbon, high carbon price signal could be helpful. And we also illustrate that the financial accessibility is a key factor here that can help speed up the transition. Yes, so that's almost my presentation. I just want to point out that in our study, we also did a lot of other investigations, such as some system dynamics studies, which I don't have enough time to explain in detail. We also investigate how on the agent level, how do different agents invest differently, and how we compare their economic performances as well. And if you are interested, okay, it doesn't show here, but the code and the full description of the model is available online on github.com/happyapm, and also you can find it on Chalmers website. And okay, this should be my email, but it doesn't show here. But if you have any question, you're welcome to contact me. Yes, thank you.
Thank you very much. In this session, this is Leire Gorroño, who is lecturer and researcher at the Mondragon University. She obtained her PhD in energy planning at Aalborg University, and before that she obtained a master in sustainable energy planning and management. And her expertise is and research interests are governance solutions for the energy transition. So Leire, you already present. It's great. So please.
Yeah, thank you, Mats. I'm trying to put it on full screen.
Yes.
Okay, there we go. So for today, I'm presenting a study that I conducted together with Jaqueline, one of the previous speakers in this session as well. And this is about getting fair institutional conditions for district heating consumers, and it brings some insights from Denmark and Sweden. So the reason why we work with district heating is because it is expected to have a lot of benefits for the decarbonization of the energy system, both when it comes to integrating renewable energies, also using heat sources that would otherwise be difficult to use, increasing efficiency, and also when implemented in targeted locations, it could lead to lower socioeconomic costs of future energy systems. It can also have several benefits for consumers, like improved indoor environments, lower risk of accidents, and less noise, and so on. So it's a technology that has a lot of potential benefits. But what we see is that even if Nordic and Baltic countries have reached some high levels of implementation of district heating, there are still large untapped installation potentials in the EU. We also see that there are several examples of poor practices by some district heating companies in different countries. And this can be things like unreasonably high prices, too high or low indoor temperatures, it can be poor customer service, and so on. So there is a risk that this will have a negative influence on consumer adoption of district heating. So if we want to really promote district heating adoption, we think that it would be very important or even essential that we develop and implement institutional conditions that safeguard district heating consumers' interests and rights. But there is quite some confusion still on how we can do this and how we can develop institutional conditions that are suitable for the particularities of district heating systems, which, as we know, are local, vertically integrated natural monopolies. Basically, what this means is that district heating consumers that are not satisfied with their district heating supplier cannot choose a different supplier. They can only choose to invest in a different heating solution. And that means that the customer lock-in effect is bigger with this technology than with other heating solutions. So what we did for our study is to review the institutional conditions implemented in Denmark and Sweden from the start of district heating until the present. And we also analyzed why different institutional configurations have managed or failed to promote fair conditions for district heating consumers. And it's this second part which is new compared to what we can already find in the literature. So why Denmark and Sweden? Well, we know that these two countries have quite big shares of district heating implemented already. These are countries that very often are used as benchmark or examples of good practice. And at the same time, they are Nordic countries that are at the most different between them, because Denmark has the highest share of locally and owned district heating owned by consumers, whereas Sweden has the highest share of commercially owned amongst the Nordic countries. And then Denmark has the one with the strictest district heating regulation with non-profit price regulation, connection requirements, and so on, whereas Sweden has a soft district heating regulation with no price regulation. So this made these two countries very interesting for us for a first step into this type of analysis. So what we did was to collect data from a structural literature review, some expert interviews, and other data sources like legal documents or archival records and so on. And we did a thematic analysis of the data following the code book that was based on two analytical frameworks. The first one is the consumer power on natural monopolies that states that consumer power has 4 dimensions: ownership power, state regulative power, buying power, and communicative power. And the other analytical framework is based on parameters to evaluate the fairness of conditions for district heating consumers with regards to product quality, customer relation quality, and heat prices. But for today, I will only present the results related to heat prices, as they are the most relevant for the findings we got. So for our analysis, we figured out that we could divide the institutional conditions for Denmark in 3 different periods. An initial one where there is no district heating regulation, then the one after late 70s where there is district heating regulation and very strict regulation actually, and then a last period where the regulation is a little softer. We can also see how commercial companies enter the game. And maybe something else to highlight from this period is that there is an increase in the communicative power that comes also from changes and improvements in the district heating regulation. So for the same periods, we tried to identify the different issues that happened in relation to district heating prices. And what we see here is that there are some policy-induced high district heating prices in the last 2 periods. There were also issues with very high prices in commercially owned district heating companies. This is something we can relate to lower consumer power or lower ownership power of consumers. It's also difficult for regulatory authorities to identify all possible cases of law infringements. And then we find quite a hot discussion in the last years about the district heating regulation, and if that's enough to actually promote cost efficiency in district heating companies with different understandings of the issue and also different understanding of what good solutions could be, and also things related to the tariff structures and if these are discouraging energy conservations in buildings. So what we found for Sweden is that Sweden started with district heating being regulated when this was owned by the local municipal companies. Then there was a period of liberalization and reorganization, which is related to the liberalization of the electricity market or the electricity sector, where there was no price regulation any longer for the district heating companies that were owned by the municipalities. There were also many systems that were sold to private companies. And finally, we have again a period where there is some regulation, a soft regulation that has focused a lot in increasing the buying power of consumers and increasing the communicative power. So again, we see some similar issues with significant increases in district heating prices in some district heating companies in this liberalization and reorganization period. There is still some debate going on whether district heating should be allowed to make profit or not, but that was of course more important debate some time ago for the second period. We have also seen that commercially and state-owned district heating companies tend to have higher district heating prices than locally owned municipal district heating companies. And again, some issues with how the district heating bills are, their complexity and tariff structures and so on. So how we can summarize our results is that despite there are quite some differences in regulations between Denmark and Sweden, both countries have high levels of local and inclusive ownership, and this can be organized as local municipal companies, or in the case of Denmark, also as local consumer cooperatives. There is quite a lot of district heating companies that apply the cost-based pricing principle. In Denmark, this is mandatory, but in Sweden, 63% of municipal companies do this on a voluntary basis. And there is also high levels of consumer communication power in both countries, not only because of the publication of district heating prices and other data that allow for comparative evaluations, but also because it's common to make use of media to report issues related to district heating and have a debate there and so on. So what we could conclude is that neither the free market approach that has been used in Sweden, neither the strict regulation are effective on their own. There is a need for high levels of ownership and high levels of communication, which are both facilitated when we have some local and inclusive ownership models. So, of course, we understand that the institutional conditions and other factors, which could even be the maturity of the sector, are different in other countries. So we do not expect that our results are directly transferable to other countries. And there will be a need for further studies, but we also think that it shows something very interesting that could be analyzed in other countries as well, with these things related to consumers' communicative power and ownership power. So this study is already published, so you can find more details in this article, which is open access. And you are, of course, also welcome to contact either Jaqueline or me if you would like to discuss it further. So, thank you.
Hello, my name is Sandra, and I have a question for the second speaker. I have a question about the agent-based model and the results that you showed here. Are they model outcomes? And did you also have a chance to validate them against real life investments? Or can you elaborate a bit on like real world versus model output?
Thank you, and thank you for the questions. My result, they're more like explorative model results. So I don't think it. At least I haven't tried or did such a comparative with real world data. But for example, the hurdle rate value we choose are based on some real data, but I don't think the results I showed here can really compare like to the what is happening, because also this model is like a simplification of what how company make investment decisions. So I think so far we are trying to figure out how to use an agent-based model to simulate companies' investment decisions. And I think we are not there yet to, because I think in reality, company make decisions based on a lot of criteria, and it's more complex and compared to how we model it. But I hope our model can, in the future, be more reflect on what is happening in the real world, which we hopefully will be more helpful to have a more real world implementation. And I think so far our work maybe is more in the field of modelers. Yeah, how to develop model. Yes, thanks.
Yes.
Yes. So I have a question, which I think is for Jaqueline or Leire. I don't know. It relates to what we were talking about before. So these more qualitative insights. What can I learn from that as a more quantitative modeler? Like, are these things that we could include in more quantitative analysis, or is that never going to happen? I'm not quite sure what the question is, but I think you get what I mean.
Thank you for the question. Yeah, I get what you mean. If you think like in 1 and zeros, then you can say that 1 is trust and 0 is not trust. And then you can model looking at how what's happened with the system, if it's trusting or not trusting. Then my perspective is that it's a little bit different from what's happened in practice. Sometimes the way that's done decisions, maybe you look at possibility of the model, and then is also sometimes several actors that are taking a specific decision of a regulation or whatever parameters that you are trying to model. So I think that it can be complementary. So it's necessary to take the quantitative and the qualitative aspects in order to, but depends in what you are trying to model. Yeah.
Okay. Yes. Just a brief question from me too. That probably goes to Leire. I'm wondering, in Denmark, we recently got a new legislation that we can now use low temperature heat sources without having any taxation. Could you comment on how that would affect the trusts in district heating?
So how would no taxation on low temperature district heating affect trust in district heating, you mean? You said?
Yes, we can now use heat from many different sources, from supermarkets, from a lot of things. The taxation rules have changed completely.
Yeah, I'm not sure we have analyzed trust levels that match. This what we did at least was more in this part related to what are the institutional conditions that we already have. I don't know if your concerns are related to different types of companies coming in as producers or.
Yes, yes, exactly.
Yeah,
And we have
I guess
PTX plants also as local producers, even in very large scale.
Yeah. Yeah, that's maybe something we could consider for future studies. Yes.
Would be very interesting. Yes, thank you.
We'll now start with session 4. Session 4, which is about technologies and development pathways in the context of the North Sea energy system transition. Next to some modeling work and also the social aspects and more political and policy aspects, there are also, of course, technology and technological questions which are really important for the transition of the energy system in the North Sea. So we also have a session dealing with that. To begin with, we have a presentation of Eliana Lozano Sanchez. She is a PhD researcher at the University of Aalborg. She will give us a presentation about modeling of HTL-based biorefineries for advanced biofuels production and the prospect in integrated energy systems. So Eliana, can you let us know that you're there?
Yes, I'm here.
Welcome, Eliana. The floor is yours.
Thank you, Dirk. I hope you can see my screen now.
Yes, we can.
Okay, so good afternoon, everyone. My name is Eliana Lozano. I'm PhD student at Aalborg University. This is the title of my presentation of today, modeling of...
Eliana, could you go to full screen? We can see the PowerPoint application, but...
Okay, where should I go? Maybe here?
Yeah, this is already better. I think this works.
Yeah, no. Is this fine? I don't know if...
Display settings. I'm getting some feedback from the from the audience. The top one.
Okay.
Hooray! That works. Thank you.
Okay, perfect. Yes, so this is the title of my presentation. Modeling of HTL-based biorefineries for advanced biofuels production. So today I'm going to talk about technology for the production of advanced biofuels. This is hydrothermal liquefaction technology, now HTL, which I'm going to explain further on. So advanced biofuels are one type of the different renewable transport fuels that are currently under study at EU level and are expected to play a role for the energy transition in the transport sector, particularly for heavy transport, so aviation and maritime. We have already some targets and legislation in place. Recently, the Fit for 55 package included aviation and shipping and specific targets for these sectors. Here we can see that the challenge is big. Actually, these technologies are expected to deploy very quickly after 2030. Advanced biofuels being used as transition fuels, and also the power to liquid fuels are going to be there. But the challenge right now is that there are not too many advanced biofuel technologies that are at a commercial scale, at a commercial level. So there are quite some at the demonstration scale. And the challenge is then to bring these technologies up to commercialization. So I'm going to talk about the HTL technology. This is hydrothermal liquefaction. Very briefly, it comprises two main steps. So we start with the biomass, and for my PhD, I work mainly with forestry residues and sewage sludge. In HTL, we have the presence of water, and we use it at very high temperatures and pressures to produce a biocrude. And therefore, we need hydrogen to increase the quality of this biocrude and to make it suitable for to be used as transport fuel. So going to commercialization, of course, we're interested in how this technology can be integrated into the system. It's not only about the biofuels, but also other products that we can integrate, such as excess heat, CO2, of also other materials that can be of use. Literature until now on HTL has focused a lot on the biofuel product. So trying to estimate what is the minimum fuel selling price and how competitive it can be with other technologies. But there are lack of studies that, for instance, look at the CO2 product, which is an interesting topic for carbon capture and utilization or storage. So we know power-to-X and negative emission technologies are expecting to play a big role in the transition. Also, excess heat from the process can be used for sector coupling. And during my PhD, I'm working on these aspects to see how these other products can have an influence on the minimum fuel selling price. So I'm doing a techno-economic analysis. Also environmental assessments. Here I show more or less the methods that I'm using or that I used. Literature study, a lot of experimental data already published or produced in-house at the research group. My modeling tools are mainly process modeling, but also coupled with economic evaluation and some environmental analysis. So as a result of my PhD, I have four journal publications, 3 of them already published. And today I'm going to tell you more about the last 2 due to time limitations. But these last 2 publications integrate also the results of the first 2 papers. The first one was more in modeling of the technology, the carbon capture step in the second paper, and in paper C and D, I did a modeling of a more integrated version based on the forestry residues and on the sewage sludge. So I will start with paper C. In this case, I looked at a centralized biorefinery with carbon capture. So in this simplified diagram, you can see we have an input, which in this case is forestry residues that we have. We have the 2 steps that I previously described. So the HTL and the upgrading step where we need hydrogen, and the box in the bottom, which says select salt, is the technology we use here to evaluate the carbon capture from the HTL gas, which is in a relatively high concentration between 60 and 80% for the lignocellulosic material. So as main products here, we have the CO2, and we also use the technology, the select salt technology for cleaning hydrogen, which is needed in excess in the process. So this hydrogen needs to be recovered for the economy of the process. And we also evaluated the production of excess heat. So the main question to answer here was what is the impact on the minimum fuel selling price and the greenhouse gas emissions for coupling the carbon capture step in the process. Here I show the cost estimation for the HTL baseline, so without the carbon capture. You see all the cost contributors there, hydrogen is a big part, is taken, the cost is taken for green hydrogen. So the cost or the minimum fuel selling price is in the order of 800 euro per ton. When we include revenues from excess heat, it slightly decreases. Then in the bar at the bottom, we see when we include the carbon capture step, so we see a slight increase in capex, also increase in utilities and other costs. However, when we include the revenues from the CO2 credits under the European trading system, we see that the initial increase that we estimated in around 8% goes down to approximately 3%. So this is, of course, something that is not too bad, 3%, but depends on the CO2 credits and also how much heat we can actually integrate with the system. This is for a base case. We look at it also in a range, different minimum and maximum values for different cost parameters. So the result is the impact between -2 and +5%. So it's still within 5% increase. And in terms of the environmental performance, we see here for a standard HTL without carbon capture is in the order of 85%. The big bar or the big part here is the hydrogen, which has still some contribution due to the electricity emission factor. But in a scenario where we have a complete green electricity and we can capture and store the CO2, this technology can perform as a negative emission technology. The result is it's also similar or in the same range to what has been published in other papers, even though there are not so many at the moment. But we see it's in the order of -20 grams of CO2 per megajoule of fuel. Yes, so I'm going to talk about the paper D. Last paper is about the sludge valorization in an HTL biorefinery. In this case, we look at a distributed configuration of HTL plants, having the Netherlands as a case study, and using the fuels for the marine sector. Again, we look at techno-economic assessment and also environmental performance relative to business as usual, which for this case is mono incineration. So briefly, an introduction on the sewage sludge treatment. Well, this is a byproduct from the wastewater treatment plants. It contains organic and inorganic matter, but also contains some things that we don't like we wouldn't like to have, such as contaminants, microplastics, pharmaceuticals. So in general, at EU level, there are different technologies that we are using right now to treat or to dispose this byproduct. Key technology aspects for a sludge case are the destruction of contaminants, as I already said, and also more recently is the issue of phosphorus recovery. So I think Matt's already introduced this or talked about this before. We need to recover phosphorus from the sludge. Mono incineration, it's one of the technologies that is currently applied that is very effective in the destruction of contaminants, and also will enable after phosphorus recovery in a later stage, but also it has the highest cost. So we're talking about for the Netherlands, it's also the dominant treatment technology, as you see here, but it's quite expensive. So we studied distributed plants here because production of sludge it's already distributed. There are a lot of wastewater treatment plants in the Netherlands, which you can see in the picture. And also previous research has indicated that implementation it's not economically feasible in small plants. Including approaching a configuration of regional plants, it's important to harness the potential of all the plants. Here you see an overall of the mass balance. So we took statistics from 2018 and used yields based on experimental data to estimate how much hydrotreated biocrude or marine fuel we could have at the end of the process. You can also see here the mineral product, which contains about 90% of the phosphorus. So phosphorus recovery is also an important aspect of this technology. In terms of the costs, you see here in the top bar, so that's only for the HTL step. The positive part of the graph, it's about the production cost, and the negative is corresponds to the sludge gate fee, which is the money you could get for treating that residue. So we see that is quite big and could largely compensate the production costs. So here we're talking a talking about a very or relatively low minimum fuel selling price, and then we will go to the upgrading step. Again, by implementing or by taking into account the sludge gate fee, the cost of the biocrude it's quite low, in the order of 650 euro per ton, which is quite positive. Something interesting to see here is that the transport has a relatively low share. So we could even try to increase the plant sizes in order to decrease the minimum fuel selling price further. Again, Monte Carlo shows that we are in a range. Yes?
Considering the time, I would like to ask you to try to move to the conclusions.
Yeah, this is my last slide.
Okay, perfect. Carry on.
Okay. Here you see more or less the range. Because we have below zero in some cases, then this indicates that there is potential for a more economic treatment compared to mono incineration. And this is finally the environmental performance. But I'm not going to talk about it. Maybe we could leave it for further discussion if someone is interested. Main conclusions of my studies are HTL has potential to be a negative emission technology without a significant increase in the minimum fuel selling price, and also for the case of the sludge treatment, it seems to be competitive with mono incineration fees, and also more beneficial from an environmental perspective. Thank you.
Thank you. We carry on with the program. Next is Abhinav Bhaskar. He is from the University of Stavanger. He was working at the University of Stavanger. He's done research into techno-economic evaluation of hydrogen-based steelmaking. Abhinav, may I give the floor to you?
Thank you so much. I hope you can hear me.
Yes, we will definitely try.
Okay, cool. Just a confirmation, can you see my screen now?
Yes.
Okay.
Could you move to presenter mode to increase the size of the screen, perhaps?
Oh, display settings. Does that work?
Yeah.
Okay,
Thanks.
Perfect. Thanks for the introduction, Dirk. I would be talking about my third paper and the final paper, and this is regarding the decarbonization of primary steel production, which we heard quite a bit about yesterday, and how the techno-economics would play out if we had a plant, a green hydrogen-based steel production plant in Norway. So before going into those details, I would just mention the strategies which could be used for decarbonizing the steel sector. The steel sector and other industries are considered hard to abate sectors where direct electrification is not possible in most cases. As we saw yesterday as well, that coal is the primary source of energy as well as used as a chemical feedstock. So there we could use two strategies. We could use demand side strategies to reduce demand of primary steel or steel in general by using material efficiency, using less material, recycling, or through material substitution. Like in the construction sector, there's a lot of talk about substituting steel with wood, for example. But apart from that, we also have measures on the supply or the production side where we could change the technology itself to reduce the emissions from the production processes. Where hydrogen-based direct reduction has been talked about quite a bit. There's an alternative of using CCS or CCUS, and also the injection of biomass directly in the blast furnaces. And one of the upcoming technologies I would say is electrolysis, where electricity can be directly used. And here also the emissions would be quite low, but this is at quite a low TRL. Just a comment on this for the demand strategies. There is a lot of discussion about these measures, but the demand for steel is going to increase because it's directly related to the population growth, and the demand would probably come more from the developing countries where the infrastructure is still to be built, and steel would be used more and more. And it's projected that the demand for steel would increase by more than 50% by 2050. So we need measures on the production side. So one of those is the use of hydrogen instead of carbon for the reduction. And I'm showing a system which could do the same for the, I would say for time purposes, I would not go detail into each of the components, but I can get quickly on the shaft furnace, which is a replacement of the blast furnace, which is traditionally being used for steel production. And here, instead of coal, you can use hydrogen as a reducing agent, which produces iron, pure iron at a temperature of 700 degrees Celsius, which can be fed to an electric arc furnace along with scrap, or we can do 100% DRI as well, and that could produce steel. So what is the energy consumption for such a system? It's close to 4 megawatt-hour per ton of liquid steel, which is slightly higher than the BF, BOF, or the blast furnace-based steel, which we've traditionally been using. And majority of the energy is consumed for producing hydrogen. And this is more than almost 75% of the total energy is consumed by the hydrogen production step. But the emissions of this system can be divided into direct emissions and indirect emissions. And the direct emission ranges, as I'm showing in this panel here, are quite low. And the indirect emissions are based on the consumption of electricity for the production of hydrogen. And here I'm pointing out some of the countries where the emissions will be extremely low because of the low emission factor of the electricity. And a point to mention here, in Sweden, there's already a demonstration plant running for hydrogen-based steels in August 2020. And new projects have been announced in various countries, including Spain and Germany. When I started my PhD, there was hardly any. And now I think we have a list of at least 30 projects coming up all across the world with hydrogen-based steel making. We did a NPV sensitivity analysis to analyze what are the main factors which affect the financial feasibility of the plant. And we found that electricity costs are the major factor which affect the feasibility. And we also did a global sensitivity analysis and got more or less the same result there, where the price of electricity was the major contributing factor. So based on these findings, we started thinking about the use of or the relocation of iron and steel industries to countries with cheaper electricity prices. And Norway was one of the choices, which is quite close to the EU demand centers and has one of the cheapest electricity prices as well. So here I'm showing the configuration where the electricity can be either purchased from the electricity markets, from the day-ahead markets, or we could sign long-term power purchase agreements. So here we have analyzed the use of electricity from electricity markets by looking at the use of hydrogen production with a storage to leverage the price variability in the day-ahead electricity markets. And the reason why we chose Norway was because of the access to cheap electricity, and because of which a large amount of aluminium producers have set up their plants in Norway. And also there is a huge demand for low carbon steel in Europe, and Norway is quite close to this region. And also one of the contributing factors was the huge offshore wind potential in Norway, which would be developed in the future. It's almost close to 12,000 terawatt hour per year, but most of it is in deep water, for which would need floating resources. To analyze this problem, we developed an optimization framework based on Python, and we used Pyomo, open source library, for developing this problem. And the objective function was to reduce the total cost of production of hydrogen. And it was a simple function where the cost vector here is the cost of electricity price per hour. And we use different electrolyzer capacities to analyze how the cost would vary. We got some interesting results. Here I'm showing the production pattern for different electrolyzer capacities and also the storage status for different electrolyzer capacities here. And these are, I would say, this is a histogram where I'm showing the frequency of hours for which you would produce a certain amount of hydrogen. So here you can see that the number of hours at which the electrolyzers remain idle increases as we increase the capacity. And this could also indicate that the steel plant can participate in capacity markets or demand response markets as well when it's available. This is the electricity price for different configuration, and this is the hourly price variation. It does not give very I would say indicative results, but when you do it for aggregated for an hour for a day, it becomes clear that when we increase the capacity, the electricity cost of production reduces significantly. And similarly for a monthly and yearly version as well. So for the annual, if you see the annual variation in total electricity cost of hydrogen production, it reduces significantly as we increase the electrolyzer capacity. But the levelized cost of production increases as we increase the capacity of the electrolyzers. This is related to the fact that electrolyzers are still very costly. And when we increase the electrolyzer capacity, we also have to increase the storage sizes. So those both are connected to each other, and that leads to an increase. But the levelized cost of production for steel, if we purchase electricity from the grid or the day-ahead market, it's substantially lower compared to if we have a corporate power purchase agreements. And here the range is almost $594 per ton, which is comparable to, I would say it's 20% higher than the levelized cost of production from baseline technologies. But with some of the companies like BMW and Mercedes and also Volvo showing interest in buying green steel by also paying a premium, this could be a reasonable cost in the future. So last slide on the conclusions. The levelized cost of production varies from almost 584 to 989 for different configuration. And participating in the electricity markets reduces the production cost by 8% compared to a plant with similar capacity if they buy fixed electricity prices. And the increasing the electrolyzer capacity reduced the operational cost. However, the fluctuations were not high enough in Norway to justify the additional electrolyzer and hydrogen storage capacity. And we also saw that if we have access to underground hydrogen storage, where the storage costs are much lower, and if you increase the capacity of storage, then it is possible to decrease the operational costs further. And that would be our, I would say, future research work. So with this, I'll end my presentation. Thank you for your time.
Thank you, Abhinav. Very relevant and also a very actual topic, especially also here in the Netherlands. So thank you for these insights. We'll move on with the program. Zhang, PhD researcher from the University of Stavanger. He will be giving a presentation on techno-economic performance of a PV battery-centered microgrid based on price-based operation strategy. Zhang, can you hear us?
Yes, I can hear you. Can you see my screen?
Yes, we can hear you. We can hear you. We can see your screen. We can see you. If you can put it in presenter. Perfect.
Okay, yes.
The floor is yours.
Okay, thank you. And I'm ES Arnan. My name is Zhang, and I joined University of Stavanger last year. And I'm going to present some results of this year. And my PhD topic is about development of a real-time optimization solution for the integrated energy systems. And currently we're focusing on the microgrid level. And as defined by the US Department Energy, and microgrid is a group of interconnected load and distributed energy resources. And the microgrid can act as a single controllable entity, and the microgrid can also disconnect with grid to run it as an island mode. Here is the schematic of microgrid, and we can see here it is the supply side. It may include the PV panel, wind turbine, and here we can see the storage side. It can include battery or other storage technology, and it also includes the demand side. And the microgrid can integrate with the main grid. And the core of the microgrid is the EMS. It is the energy management systems. And why we research microgrid? Because microgrid can run in the island mode. It will be suitable for the rural region, and the microgrid can also reduce the transmission and the distribution cost. And it also offer because microgrid can run in a very flexible way, and it offers the energy efficiency by responding to the real-time market price. But we also meet a lot of challenge for microgrid in the design phase, because there are so many types and so many types of generation and storage technology, like PV, wind turbine, microgas turbine, etc. And we need to decide which type and the size of the technology. And we also need to meet the energy efficiency and the economic environment, this kind of requirement. And in the operation phase, we also need to decide when to run and stop the equipment and how much capacity each equipment should generate. And we also need to decide when to charge or discharge the storage technology. And finally, we want to get the minimum operation cost and emission. Here I list the two example scenario. The first one is like an organization want to already get the specific location, and they have some renewable generation target. It will be the 30%. And how should they spend their limited capital resources to get the goal? And another scenario is organization interested in PV and energy storage. They want to know whether this kind of combination economic feasible, and if so, how should they operate the energy storage? Here we are going to develop a toolbox to answer the questions in these scenarios. Here is the methodology, and it will start from modeling, and we are going to develop a model for various technology. It will include PV, wind turbine, microgas turbine, etc., battery, thermal storage. And then we will have some operating strategy like load following, cycling charging, combined dispatch, and predictable control. And with the help of the operation strategy, the energy system can run for 1 year, usually 1 year. And then we will get the simulation, and like the dispatch result. It can be hourly or in the minute level. And we can also get economic and emission result. And then the simulation result, part of the simulation result will be regarded as the optimization variable objective. And then with the help of the optimization algorithms, we can get the optimal sizing solution. For the modeling, here we consider both physical based and the data driven. Physical based, we are going to use the modelic language. And here it is one application of the methodology. It is a techno-economic performance of a PV battery centered microgrid with price-based operating strategy. Basically, it is a sizing method for PV battery systems. And here, I consider the location in Cardiff in UK, and it is applied for a residential house. Here we can see the electricity load for 1 year and the weather information for 1 year. It includes the ambient temperature and the solar irradiance. And here is the electricity during the day. I got the data from one paper, and during the beginning of the day, the price is the lowest, and during the afternoon, it is a peak time of the electricity price. And here are the two main component information. And the first one is PV. I got this PV information from a Japanese brand, and this is the main parameter of a battery. Because we need to run the PV battery for system for 1 year, so we need to have some operation strategy. Here I will compare two different operation strategy. First one is load following. The second one will be the price-based strategy. Okay, for the load following strategy, the strategy will start from compare the PV generation and the electricity load. If the PV generation is higher than load, so the strategy will consider to charge the extra power to battery. But before that, the strategy will compare the SOC with the maximum value. If the SOC is lower than the max value, then the power will charge into battery. But if the SOC is equal to max value or higher than max value, the actual power will be wasted. Coming to the starting point, if the PV generation is lower than electricity load, the strategy will consider to discharge the power from the battery. But before that, the strategy also need to compare the SOC with the minimum value. If it is lower than the minimum value, it means the battery cannot discharge because it will hurt bad for its health condition. So strategy will decide to purchase electricity from grid. But on the if the SOC is higher than the minimum value, then the battery will discharge to meet the electricity demand. And for the price-based strategy, there are main difference. The first one is here. This new strategy always compares the strategy SOC with the max value, and if at the same time if the price electricity price is lower than the set point, and the battery will be charged. And another difference is here. If the SOC is lower than the minimum value, and at the same time, if the electricity price is higher than the set point, the battery will discharge. Basically, this new strategy can charge the battery during the low price and discharge the battery during the high price. Here is a model. This is a developer in the Modelica environment. And here is the operating strategy. Here is the economic calculation. And for the optimization part, the objective will be the life cycle cost. It will be 25 years cost, and it will include the PV capital fees, operation and the maintenance fees, and the battery capital fee and the replacement fee, and the electricity from the grid. And there are two main optimization variables. The first one is PV capacity and the battery capacity. The optimization algorithm will be the SQP, and I use the Daimler optimization library for optimization. Here is the optimization result. For the case one, it is a load following. We can get this number of life cycle cost, and on the right side it's price-based. And basically, the price-based strategy can save more than 7% of a life cycle cost. And here, at least typical day under two operate strategy. The left one is the load following strategy. We can see the blue line is the PV generation, and the green line. The blue line is the PV generation. The green one is the load profile, and the black one is SOC. As we can see, is the PV generation is higher than the load profile, and the SOC will increase until its max value. And if the PV generation is lower than the electricity load, the battery will discharge and the SOC will decrease until its minimum value. On the right side, we can see at the beginning of the day, the SOC will be increased because it is a low price period. And on the afternoon, and the battery will discharge because it is a high price period. Here I list the SOC for whole year. As we can see, for the load following strategy, during the springtime and the winter time, the SOC will always remain the constant because during this time, PV generation will always lower than electricity load. But for the price-based strategy, the SOC will always change. So this kind of strategy can utilize PV, utilize the battery capacity well. Okay, thank you. Thank you for your time. Thank you for your listening. This is my presentation.
Then we'll have the final presentation. Srini Santakumar, associated to the University of Groningen. Srini.
Hello.
Yeah, hello. I can hear you. I cannot yet see you. I can see your screen now.
You see the presentation? Yeah.
Welcome. You were telling us about the technological learnings of offshore renewable energy technologies and recommendations for scaling up, right?
Yeah.
Perfect. Can I give the floor to you?
Yeah, sure.
Okay, well, go ahead.
Good afternoon, everyone. I'm Srinivasan. I'm one of the ESRs hosted at the University of Groningen. Today, I will talk about the technological learning of offshore renewable energy technologies and recommendations for scaling up. So in my agenda, I have two components to talk about today. First, I will introduce my PhD, what are the objectives and methods, and I will sort of give like 4 recommendations or key conclusions from my research. It's not an exhaustive list, but considering the time period of the presentations, I like to convey some important points I have analyzed in my PhD.
Sorry to interrupt, but we don't have any visual of you. Could you perhaps turn your camera on?
Yeah, just.
Thank you.
Could you see me?
Yes, perfectly.
Yeah.
Thank you.
Okay. So first, my objective of the PhD is to investigate how key offshore renewable energy technologies might improve in terms of improvements, scale-up, and implementations. And the technologies I have shortlisted are kind of focused on includes offshore wind, fixed bottom and floating, wave and tidal stream technology, and also biofuel production from the seaweed. In terms of methods, since my objective is to consider technological learning, I didn't kind of narrow down into a single methodology. I sort of looked around different methodologies. One is learning curve. It's not a law, but it's an empirical observation which says the unit cost of a technology or product decrease at a constant percentage for every doubling of its cumulative output. Then the second methodology I've used is the bottom-up engineering cost modeling, where you can model a technology cost in terms of different cost subcomponents, and you can narrow down the cost centers which is affecting the most. The third one is I also try to review the theoretical frameworks available in the literature, for example, innovation theory, growth models to understand the theoretical basis for the technological learning. So I kind of used a mixed method approach to understand the technological learning of the offshore renewable technologies. So I'll go ahead with the recommendations or conclusions from my research. First one is to kind of emphasize that technological learning happens in sequential stages. For example, if there's a new innovation coming to the market, it starts with a prototype or demonstration, where there will be like a lot of different designs experimenting in the market. And then in the next phase, some sort of mainstream design convergence will happen and small scale demonstrations will go through that. The next one is the large scale commercial operations of the technology, which could be upscaling phase, and then the next one is the growth phase. In the growth phase, it will be purely not only it will be a mainstream technology in the core market, but it will also start diffusing into the secondary and tertiary markets. Looking at this theoretical framework, when you are trying to analyze the technological learning, the data availability also varies across each stage. For example, in the prototype demonstration, you have to rely purely on the analogous technology cost informations, but going period by period, you will also get some price data, but it's also, we will have to understand there will be some market dynamics, because at the prototype, there will be few companies, and then there will be new market entrants, and there will be some sort of market shakeout phase, and then there will be a market consolidation. So going through this life cycle, we also have to understand how the profit margin happens between these stages. So this was kind of a theoretical framework we developed, and we tried to fix the offshore technologies at each stage, considering the development. So we try to fix the offshore wind at the upscaling phase, and also the wave and tidal and the biofuel production from the seabed at the prototype and demonstration phase. So the next one is we apply this framework to understand what's happening with the fixed bottom offshore wind until 2020. So we try to use two parameters. One is the cumulative capacity, which is a proxy for the market growth in the European markets. And the next one is the turbine rated power, how it has been developing over years. So it's proxy to understand the units upscaling. When I mean unit upscaling, it's part of the economies of scale, but it's not exactly like a manufacturing scale of economies. So unit scale economies in the sense, I mean, if you increase the capacity of the unit size, for example, generation capacity of the wind turbine, you will reduce the fixed cost of the particular unit. But if you take a modular technology and start manufacturing in large numbers, you will reduce the overhead in the manufacturing unit, and we call those things as the manufacturing scale of economy. So there is two types of economies of scale, and that's what I was trying to differentiate with the offshore wind turbine. So if you're going through the formative phase of offshore wind, it has been faster because it's more or less around 10 years. It is much lesser compared to the other technologies, what we have seen in the, for example, coal or combined cycle power plants, which has taken several decades with the formative phase. The faster formative phase is due to the fact that it is based on the onshore wind and also oil and gas industry practices. Then they were actually deploying onshore wind turbines in the formative phase. Then they were running out of problems. So during the upscaling phase, they started developing wind turbines specifically for offshore conditions with higher rated capacity. For example, I'm sure you have seen pictures of comparing offshore wind turbines to tallest buildings in the world and similar sort of that. And there is a growth phase. Once the technology has proven its viability in the market, there will be market pull mechanisms to increase the capacity in the energy system, and also it start to diffuse into the secondary market. A good example is offshore wind is moving from European markets to the Asia Pacific region nowadays. And in the formative phase, the offshore wind has taken a lot of practices from the onshore wind and oil and gas industry, but also there is a very spillover effect from going from offshore wind to onshore wind. It includes the recent developments of introducing newer platforms, deploying offshore wind technologies in the onshore wind turbines to increase its capacity factor. So this is the case study where we try to separate the developments in different phases so that we could understand what are the cost developments and what are the learning mechanisms happening in each stage. So, and our second point is to emphasize the financing cost. Financing costs play a significant role in the development of large-scale energy technologies. So, the picture shows a LCOE estimation for a wind farm, fixed bottom offshore wind farm, which could come online in 2022 or 2023, which has a capacity of 1 gigawatt. And I try to show the technology costs and the financing expenditure at different discount rates. So when I say financing expenditure, it is driven by three factors. One is cost of capital or discount rate, and the technology costs which need to be financed. And the third one, the capacity factor, which discounts all the technology costs in the lifetime revenue. So we will only focus on the cost of capital for now, keeping all the other things constant. As you can see, going from 4% to 10%, the LCOE increases by 59%. So when you look at the cost of capital, it's driven by base interest rates in the economy, which is related to the macroeconomic factors. And there is also the premiums expected for debt and also equity. So when the technology is new, there will be a lot of investment risks, but as the experience effect happens,
the development will also decline. And also, once the investors became very certain about their revenues, both the premiums expected by the investors will decrease. Those are the major factors for the cost of capital. We also try to understand what's happening in the fixed bottom offshore wind. So we try to model that cost of capital for different countries in the European region. Our major observations were after economic crisis in 2008, the base interest rates have decreased drastically. And also there has been targeted incentives, for example, CFD contracts or SD plus in Netherlands. And also there is a lot of market competition introduced by the auction mechanisms, and also increased confidence in the technology has decreased the debt premiums and expected return on investments. If you can see I don't know if you can see the cursor, but in the top right, if you see the UK from 2000 to 2010, the policy mechanism they were using is ROC, which it's called Renewable Obligation Certificate, but they have like a uncertain revenue model comparing to the Belgium, where there's the green certificates, or in Netherlands, it's some sort of fixed feed-in tariff. So after that, they have changed that ROC to the CFD contracts, which provide much better certainty on the revenues for the investors. So it becomes more competitive in the later periods. That was the second point. For the third one, so when I mentioned the financing expenditure is based on 3 factors. One is the cost of capital, which is discount rate. And there is also the third option, which I mentioned about the annual energy production or capacity factor. So I would like to mention understanding the nature of the energy source and also the technology characteristics beforehand can be beneficial in designing effective market policies. So the figure on the right shows the development of the capacity factor for offshore wind farms deployed in the European markets. So it has increased from 30% to almost 50% in 2020. So it's not purely because of the site with better wind resources, but it's also because of the technology development. So we are seeing like 10+ megawatt turbines with the really tall uprights and also larger rotors, which increases the capture efficiency. So adding to the capacity factor, adding to the cost of capital, capacity factor also plays a great role in reducing the levelized cost of electricity. So we also looked at the cost outlook, what could happen for the fixed bottom and the floating wind. In both areas, the capacity factor has played a greater role in cost reductions, adding to the technology cost in the floating wind. Also, you can see the financing expenditure effect from floating wind, where when the technology is new, there will be a lot of investment risk. So all the investors will be expecting a higher return, but after having experience effect, the returns will also decrease, similar to what we have seen in the fixed bottom offshore wind. So, but this is the nature of the wind energy source, but it's not same for all the energy technologies. So you can't scale up the devices for all the technologies, for example, solar PV. So we also need to understand the characteristics of the technology and also the nature of the resource. The next point is like broadly, we can classify the characteristics in 2 ways. So the technologies which can have the unit scale economies and technologies which cannot have unit scale economies, or simply you can call them as modular technologies. So for the technologies with unit scale economies, a good example is offshore wind and also onshore wind, for example, combined cycle gas turbines. So its development sequences, first they will be experimenting, and there will be unit upscaling, and then after it becomes saturated, there will be purely learning by doing, and then it goes into maturation. So in this way, there will be like a lot of R&D happening within the institutions or majorly only in the industry. So even though the learning rates for the investment cost can be low, but the performance improvements and also the cost reduction in other components will result in higher SUV reduction. On contrary, if you take the modular technologies, since it is not capital intensive, there will be faster standardization of the technological design, and the learning by doing, or else you can call it as a manufacturing scale of economies, will already kick in faster. So they are historically, you can see learning rates more than 15% in the investment cost, but the performance improvements and the cost reduction can be limited. So I will try to explain the nature of energy resource understanding using the example of wave and tidal energy system.
So the figure shows the number of both of the technologies are in the prototype and demonstration phase, which doesn't have a clear large-scale commercial project yet. But for the tidal energy system, almost most of the developers have converged to a design similar to wind turbine. However, we can't scale up the turbine similar to wind turbines because there will be like a water depth limitation. So you have to give clearance for shipping lanes or these kind of things, which will introduce a cap on the performance itself. On contrary, for the wavelengths, the wavelength, most common design is the point observer, and which when the wavelength of the wave is smaller, it limits the developing large-scale devices. So you will only see devices less than 1 megawatt or 2 megawatts. So these devices are expected to be modular, on contrary to the wind turbines what we are seeing now. So one thing is to understand is not only to understand the nature of the energy resource, but we also need to understand the characteristic of technology so we can strike a balance between R&D funding and market pull incentives. So these examples are to emphasize the market pull incentives is not always the answer. My last point is to understand, to show for the offshore wind system, grid connection costs also play a significant role in planning of the future offshore energy systems. So the figure shows the levelized cost of transmission matrix for 700 megawatt offshore HVAC radial connection. So there are three influencing factors. One is the distance to shore, utilization factor or the capacity factor of the wind farm, and also the skill of the transmission. So for example, if you're deploying a substation at offshore, you need to lay the cables, and there will be like a lot of fixed costs. So the economics of the scale will also play a greater role, and that is the relation shown in the second figure. I only model until 100 kilometers because after 100 kilometers, HVDC is expected to be competitive. So you can still use the HVAC, but it will be more expensive than the HVDC because we need to compensate for the reactive power losses. So in the previous presentation, a lot of people have raised concerns about the offshore spatial constraint, cable routing, and also we need to manage the high share of renewables onshore. So the transportation is not always going to be electricity. Maybe we can convert it to the hydrogen or some other liquid fuels, and also the interconnected capacity expansion between countries in the North Sea. So these requirements call for an integrated offshore grid, and which requires a system level planning, which is currently absent. So those are the 4 key points I'd like to mention. Thank you for your attention.
We have some room for questions from the audience, either online or here in the room. I'm not sure whether there are any questions. Yes.
Yes, I would have one question to presenter number 3. That was Qian from University of Stavanger, talking about the microgrid optimization. I have one question. Did I get you right that these microgrids are basically connected to the major electricity grid? And how do you consider the situation of your optimization at the microgrid level as compared to the storage options that you have at the central level? I ask this question because we have a number of studies and simulations where we find that in a connected system, we will find the need for more centralized large storage, and that we can use kind of the levelization of the variable renewables across a larger area. So if you only look at the PV at the local level, you will have maximum variability, and you would work with your battery right against that. Wouldn't that increase the need for storage at the local level dramatically as compared to a connected system?
Thanks, Professor. Thanks for your questions. In my case, currently I consider it a microgrid level. I mean, especially for the storage side, it is only the battery, not for the central level. Why microgrid? It is quite popular. I think it is very convenient to storage, especially in this small size, because central level size right now it is still has some engineering problem. A lot of researcher also put a lot of effort on that. So this is the right attractive part of the microgrid for storage set. And for my optimization, I already get the electricity load, so I can decide which part I can use PV generation to meet the load, and which part I can use battery to meet the load. If there is extra power from PV generation, I can store it into the battery. So this is my main idea. How to do that? I developed a model for different components for PV and for battery. Then I can decide using the operating strategy. I can decide when to discharge and when to charge, and to meet the final economic result. This is the main idea of the application.
Thank you. Another question? Oh, two.
Thank you. I want to have a follow-up question to Sam speaker, to Zhang. Thanks first for the very interesting presentation, and have maybe a more specific question about the model. I think it's very interesting, okay. Like how you decide that how do you decide when to discharge and how much to discharge? I mean, for example, if I have enough electricity stored in one of my battery, and I see that the electricity price is higher than the my expectation, then I choose to discharge. And I'm just wondering how do you decide, like, at which time point you to discharge, because the electricity price can change over time, right? If I discharge, maybe now it's 1 cent per kilowatt, I can discharge, I can make money, but maybe next time step it's gonna be 2 cents per kilowatt hour, then it's more profit. I mean, do you consider, how do you model this? Thanks.
Okay, yeah, thanks, Jinxi. Thanks for the question. And in my case, the electricity is changed, but it has the fixed philosophy for whole days. So I know which period it is a low price, which period is the high price. This is the electricity price. And for the modeling aspect, for the PV model, if I know the weather information like solar irradiance and ambition temperature, the model can predict the power generation of the PV. So I can predict the PV generation. And also in the model, we already know the electricity demand. It is the input of the model. So I can compare the electricity demand and the PV generation. And if the PV is higher than the demand, then we can charge the actual energy into the battery. And for the battery, there's a very important criteria. It is a state of charge, SOC, and the SOC will always remain within the max value and minimum value. So if it is SOC is lower than the max value, so we can charge into the battery. This is the basic idea how to charge and discharge.
Thank you. We have another question over here.
Yeah, maybe continuing on the same discussion. I think like using microgrids is it's definitely a solution for certain areas, and I think those areas are mostly located in, if they are too far from the transmission grid, for example, if it's going to cost too much to expand, yeah. And I think you already mentioned this in your presentation, when the benefit of expanding the transmission line is going to be too costly as compared to establishing a microgrid system. But the idea, but I think there's the discussion of how many communities exist across, I suppose in Europe, it might be less, but it might be a more interesting solution for countries in developing countries as opposed to Europe, where maybe those communities are mostly well interconnected with the grid. But I think this is a study in itself to identify how many of these communities exist around the world, and this might be a solution for them.
Okay, yeah, thanks for comments. Yeah.
Was that a question or was it an observation? It's more of an observation. Okay. Are there any other questions? One, I would say this is the final question, then we head on to the coffee break.
Okay, don't want to keep you from the coffee break too long, but Abhinav, I have a question concerning the hydrogen steel. I think that's going to be one big area. Now, critical for that will be first the comparison of today's steel price to your estimated steel prices, and then the question, how much would a ton of carbon emission need to cost to make up for that difference as you have estimated that? Just can you give me approximately an order of magnitude for that?
Yeah, thanks for the question, Professor. The answer to the first question is the cost estimation is almost in the range of 25 to 30% increase from the base cost at present. And the cost at which we can compare the baseline technology with hydrogen-based steel would be in the range of $55 to $75 per ton of CO2. So we are already at that range. So the marginal abatement cost here would be 60. So we are at the level, and that's why it's getting so much traction. And this also has to be understood in terms of the larger hydrogen picture, where hydrogen is, the cost for hydrogen is going to reduce significantly. The electrolyzer cost will have a lot of technology learning effects, and part of which has been, I think, just a comment on that, part of that has been missed from the developments from the chlor-alkali process, which additionally uses electrolyzers. And in China, we have very low electrolyzer prices. And the move towards is already happening from coal to hydrogen, especially projects in Inner Mongolia, for example. Now they are converting from coal-based gasification for ammonia production to green hydrogen-based ammonia production, because to reduce the renewable curtailment, but also because they have access to very cheap electrolyzers. So this is happening, and I think we should be very aware of these developments on the electrolyzer side as well.
Fair enough. Thank you, Abhinav. Thank you all the other speakers for your presentations and also your responses to the questions from the audience. We'll be having a brief coffee break till around 4 o'clock. And then we will have the final session of today with our last keynote speaker and a very interactive debate. So I will see you in around 15 minutes.
And we have, fortunately, found Hans Koenen from Gasunie willing to give a final keynote presentation. I think that's very appropriate. First of all, Gasunie is a full-blown secondment partner in ENSYSTRA, so they're very aware of the program. And on top of that, they are really in the middle of the transitions that we are discussing, that ENSYSTRA is dealing with. To get gas meets wind is in the title. This is a big theme in the north of the Netherlands, and for Gasunie, very much oriented towards hydrogen as the key carrier of the future, and that's where the organization, the company, the institute, you can call it many things at the same time, is fully focusing on, but also many other areas. So I think, Hans, you can introduce your specific activities that you have today, because I'm also interested to know what you're busy with at this very moment, except for the presentation. But I leave the further introduction to you, and we will listen very carefully to your presentation.
Okay, thank you, Andre. Can you all hear me? I hear some background.
Loud and clear,
okay.
loud and clear.
And what do you see in the screen? Do you see myself or do you see the presentation over there?
I see you with a very nice car in the background.
Yeah. Indeed. Now, and thank you very much for giving me the flexibility to talk to you via Microsoft Teams. Actually, I'm now traveling from Berlin in this beautiful car, but of course now I'm at the parking place to give this presentation. But I was in Berlin to talk, amongst others, about hydrogen in Germany, and I'm now on the way back. So thank you very much for giving me the opportunity to speak to you about all the nice developments in the Netherlands with regards to offshore developments, and I will specifically talk, of course, also about the role of Gasunie in that respect, about hydrogen and CCS amongst others. Can somebody share the presentation on the screen then? Yeah, great. Yeah, I can see it. Okay. Maybe can you flip to the next chart, please? Yeah, that's more or less me. For those people who don't know me yet, my name is Hans Koenen. I'm working for Gasunie, and I'm responsible for corporate strategy and corporate business development. And actually, that's quite a challenging job nowadays, because when you look to the business development of Gasunie, we work on a lot of projects, not only on hydrogen, but also on biomethane, heat project, and also CCS projects. So the portfolio of myself and my team is extremely full, but with all nice and challenging projects. Can you flip to the next slide? Yeah. For those people not yet knowing Gasunie, Gasunie is a European energy infrastructure company. So we are not active in trading and production of molecules. We are an infrastructure company, and our core activities are the transport and storage of natural gas, green gas, and hydrogen in the Netherlands and the northern part of Germany. Now, this sounds as a very broad scope, but nowadays, and I will come to that later, we are actually mostly transporting natural gas. But as you can see over here already in this picture, a couple of years ago, we changed our strategy, and we said within Gasunie, we should transform ourselves from a natural gas transport company into a broader sustainable energy infrastructure company. So that's also the reason why we're so busy at this moment in time with a broad portfolio of infrastructural projects. And we will come to that later on. Can you flip to the next slide, please? Yes. This is actually Gasunie today. Gasunie, as I said, is an infrastructure company. We are owning and operating a huge network, more than 15,000 kilometers of high-pressure grid. That's a lot. And a large part of that pipeline network is located in the Netherlands. That's about 12,000 kilometers. We have also a transmission network in the northern part of Germany, connecting amongst others on the Nord Stream 1 pipeline coming from Russia, but also to the Norwegian system. And in the Netherlands, we are also connected to the UK via an interconnector pipeline. And this is more or less, in a very simplified way, our network. But it's not only a network of pipelines we are operating. We have also a terminal for liquefied natural gas in the Rotterdam area. We have some salt cavern storages in the northwestern part of the Netherlands. And we are building there also a nitrogen installation at this moment in time, because of the fact that we stopped the Groningen production, the production of the Groningen gas field, and we are replacing that by the import of natural gas from Norway and Russia, but that has to be converted into Groningen quality gas, and we do that with nitrogen, and therefore we are building a nitrogen installation at this moment in time. But you also see in the left hand corner on the bottom, you see a hydrogen pipeline, and that's quite interesting, although it's still a very small project. We are transporting their hydrogen from Dow Chemicals to Yara, and that's only a 14-kilometer pipeline, But what's interesting of that pipeline is that it's a retrofitted natural gas pipeline. So there are many discussions, logically, about the possibility of transporting hydrogen via existing natural gas pipelines. But we already do that as Gasunie. We have transformed, retrofitted that pipeline 3 years ago, and we are transporting that hydrogen already for 3 years without any major problems. And that's quite important because by demonstrating that, we can also make the next step later on to have a full-blown hydrogen network in the Netherlands and abroad. Can we go to the next slide, please? Yes. And this should be then Gasunie tomorrow. And tomorrow is not that far away. We are an infrastructure business, and that sometimes the lead times of developing new infrastructure, they take a couple of years. But this could be very well a picture, let's say, towards 2030. And what you see over here is indeed that we will be transformed in a broader energy infrastructure company, not only active in the transport of natural gas, which will probably still take place in 2030 and maybe even a lot longer, but we are also active in the CCS projects. What you see over here, we'll come to that later on. The Portos project, for example, in the Rotterdam area, we are active in the heat transport. I will come to that now later on as well. But we are also active in the hydrogen infrastructure, in hydrogen infrastructural projects, not only transporting hydrogen, but also storing hydrogen in salt caverns. So that's a huge portfolio which we are going to develop in the coming couple of years. Talking about the first final investment decisions, we will take the first final investment decisions on a couple of these projects already this year and probably also some of them next year. And this is really a great step forward because today we are talking about offshore developments. And when you look at offshore developments, at this moment in time, it's mainly offshore wind developments. And that should go on, and that should even accelerate. But probably also other claims will be put on the North Sea, like storing CCS, CO2 via CCS infrastructure. Can we go to the next slide, please? Yes, and then I would like to elaborate a little bit more on the Gasunie project, also in relation to offshore wind developments, because that's the topic of today. Can I go to the next slide, please? Yeah. When you, no, let me put in another word. What we see in the development of hydrogen infrastructure, we describe more or less as a kind of a quadruple jump. So we need to take a hop, then we need to take a step, and then we need to make big jumps into the future. And when we talk about hydrogen, we do think that we should start by preparing the market, by promoting electrolysis, and also, of course, to applications in industry clusters. So when we talk about hydrogen developments, it will probably start within the different industrial clusters in the Netherlands. And we are already working on that very intensively, and not only as Gasunie ourselves, of course, but also many industries are working on the transformation towards partial hydrogen processes. For example, Shell is already developing a 200 megawatt electrolyzer in the port area of Rotterdam, but also other big players and also smaller players are already working on green hydrogen production facilities and also in working on applications in the industrial clusters. And having said that, then we should make the next step, which is also planned in the coming years. And the planning is that we will develop some regional infrastructure, starting in these different industrial clusters, as I said before. And what you see over here is that we will probably start with the development of regional infrastructure, hydrogen infrastructure in the northern part of the Netherlands and also in the southwestern part of the Netherlands. And why is that? Because in the port area of Rotterdam, of course, what you know is that there is the big chunk of the industry located, with more or less 20% of the CO2 emissions in the Netherlands. And why are we also working on regional infrastructure in the northern part of the Netherlands, and northeastern part of the Netherlands? Now that has to do, of course, with different reasons. One is that there are a lot of pipelines available coming there with the stop of the production of Groningen gas in the Groningen field. A lot of pipelines and a lot of capacity come available, which is easily available for the transport of hydrogen. But what's also important over there, in the northeastern part of the Netherlands, the salt caverns are located over there, which are also able to accommodate the storage of hydrogen in the future. And when we have developed this interconnections between the different industrial clusters, then the next step will come. It's not only the cluster of the connection between the industrial clusters, but even more important, these clusters will also be connected to the salt cavern storages and will be connected to the networks abroad. So we will have interconnections with Germany, we will have interconnections with Belgium. So that's more or less how we see the hydrogen quadrilateral development from infrastructure perspective. Can we go to the next slide, please? Yes, and it does not stop in 2030 because, as you all know, in 2030, according to the climate agreement, we should have realized more or less 3 to 4 gigawatts of green hydrogen. And that is still a lot, taking into account that nowadays, I believe the biggest electrolyzer is only 20 megawatts. So we need to scale up drastically to reach even this 3 or 4 gigawatts. But after 2030, we need lots and lots more of green molecules and green hydrogen. And that's also what we are talking about with the ministries. We need to prepare ourselves not only for this half a marathon until 2030. No, we already need to prepare ourselves towards the final and full marathon to 2050. Can we go to the next slide, please? Yeah, I was already talking about this hydrogen backbone. And here you see the rough planning of this backbone. What I said before, we will start within the industrial clusters. And the aim is to have all these industrial clusters connected with each other and with the storage facilities in the northern part and with our neighboring countries in 2027. Which is very nearby for a company like us, taking into account the development of hydrogen. And to have it realized, we need to do a lot of work, and we needed also the support of the Dutch government. And probably you have heard about it, but on this very Tuesday, the government has decided to donate, to give Gasunie more or less 750 million euros to develop this whole hydrogen backbone. Now, total investment of this hydrogen backbone is 1.5 billion. So we will also invest ourselves 750 million euros, which is of course at stake, because if this whole hydrogen development will not be realized, then also for Gasunie is something at stake. But I do think that's a very good and very positive sign from the Dutch government that they made this step, and with this step, they more or less also help us in solving the so-called chicken and egg problem. Because with this infrastructure available, demand and supply can be connected. So that's a very big step. And what I said at the start of my speech, yesterday I was in Berlin, and I can tell you that the Germans were really jealous in this big step forward in the Netherlands. Today the topic is, of course, offshore developments. And what I said, we are investing in this infrastructure, but this pipeline needs to be filled with green hydrogen. So our very urgent call to the government is also to develop much more offshore wind, because we need this to produce this green hydrogen. We need to have it to fill our pipes, but of course at the end the customers they want it, and it's clear that in the industrial cluster there's big demand, potential demand also for hydrogen. Yeah, there's of course a big debate about offshore wind, but we as Gasunie embrace the fact that the Ministry of Economic Affairs, that they want to stretch their targets for offshore wind. They want to develop 10 gigawatt extra offshore wind towards 2030, which is also really needed in front of taking into account the required 55% CO2 reduction. So we do really welcome that additional goal of the Dutch government and the Ministry of Economic Affairs. Can we go to the next slide, please? I was talking about the H2, so the hydrogen backbone, but what are we doing also in the north in respect of that developing backbone? In the northern part of the Netherlands, we are working together with partners on the North H2 project. And the North H2 project is dealing with the integrated development, the large-scale production, transport, storage, and supply of green hydrogen. And that's really what's needed, because what I said, we can solve the chicken and egg problem by investing in the infrastructure. But to make it really a success, we need to develop the whole integrated value chain. And we are working on that together with our partners, Shell, RWE, and Equinor, and together also with Groningen Seaport. This is really a big project. It's one of the biggest large-scale hydrogen projects. And we're planning to have 4 gigawatts of green hydrogen produced, to have it realized in 2030, and it should scale up to 10 gigawatts in 2040. That's ambitious, but taking into account the climate goals that we will have to realize, and the time it will take to develop this full value chains, I think it's urgently needed that we make this kind of big steps. And are we then satisfied? No, probably not, because we have to do even more, and that is shown in the next slide, please. Because in the next slide, I would like to talk about future developments on the North Sea. Probably you have heard about North Sea Wind Power Hub. In North Sea Wind Power Hub, the original idea was to develop a big offshore artificial island, an energy island, where electricity from different wind parks could be connected to, and where also offshore hydrogen could be produced. Now, in the meanwhile, we have studied a lot on this North Sea Wind Power Hub artificial islands, and together with Energinet from Denmark and TenneT, we concluded that it is probably a much better idea to work on so-called hub and spoke projects, which is not one single big island on the North Sea, but probably more smaller 10 to 15 gigawatts islands, which could be developed for connecting offshore wind parks and also offshore hydrogen production. And what you also see is that especially in Denmark, they are progressing quite fast on that. They have really concrete ideas already of developing an offshore island in the North Sea on the one hand, but also in the Baltic Sea, in the so-called Bornholm Island. And even this morning, I had a call with the Danish ministry and the Dutch ministry, so they are progressing quite fast on developing this artificial island in Denmark. But as said, does it stop there? No, probably we will need several islands. And that's also what we think as Gasunie, together with TenneT, we should aim for, also in the Netherlands. And that's what I would like to show you in the next slide. What we probably should do is to explore the development of energy islands also in the Dutch continental shelf. Because we need a lot of energy. The Netherlands is a very energy intensive country. Northwest Europe is very energy intensive. And taking that into account, we do foresee that there is a need of energy islands. Can be real artificial islands, but can also be, for example, done in a caisson construction or whatsoever. We do think there is a need, and I think I invite all of you, and also I also invite the Dutch government really to investigate the possibilities for that, and that can have the scales of about 10 to 15 gigawatts. And this really could support and should support our climate targets and ambitions. And that's the next step beyond, I think, the connection of individual wind parks with the onshore grid. Next step is indeed hub and spoke islands where different wind parks can be connected to and where also offshore hydrogen production could take place. Another important element with regards to the development of CO2 neutral infrastructure is CCS, and that's what I would like to elaborate on in the next slide. Next slide, please. Because as Gasunie, we are also working on different CCS projects. I think the most advanced project at this moment in time is the so-called Portos project, where we want to capture and transport CCS from some industrial clients in the port area of Rotterdam to the P18 empty gas fields in the North Sea. What you don't see here in this slide is the project Athos, which we are also developing. But that was the capturing of CO2 from Tata Steel and bringing it also to empty gas fields. We have decided recently, after the announcement of Tata Steel, that they will switch over to hydrogen in the future, that we will stop this Athos project. So we are not further developing a CCS project at this moment in time for Tata Steel and for the North Sea Canal area. Another development is the so-called Aramis project. Aramis project was originally the project from Total and Shell, where they want to build up an integrated CCS value chain, capturing their CCS on their plants in the Rotterdam and the Zeeland area and bringing it to some empty gas fields in the northern part of the North Sea. In the meanwhile, we, together with EBN, have joined this consortium, and we would like to further to develop this CCS integrated value chain together with Total and Shell. And that CO2 can be transported to these fields by pipeline, which you see in this slide. But what can also be done is transported partially in a liquid form to the Maasvlakte, to Rotterdam, and then further on transported offshore to these empty gas fields. And this makes it attractive, for example, for customers in the Gemmelot area or even in the Ruhr area to bring the CO2 in a liquid form to Rotterdam, to the Maasvlakte, and then transport it offshore to the empty gas fields. On the last slide, I will give you more insight in the Portos project. Can you please switch over to that? Yeah, over here you see the Portos project, and when you click some other, when you give some other clicks, yeah, then you will see the partners involved in that. The partners in this project are EBN, Gasunie, and the Port of Rotterdam. We are developing this project already for some time, and we are almost there to take the final investment decision. That will probably be taken in the first quarter of maximum in the second quarter of next year. And when you give it another click, yeah, then you see the customers over here. There are some big customers which will transport their CO2 via the to be planned pipeline and via the offshore pipeline to this E18 field. This is the first step, and the next step should then be the further development of a kind of national CO2 system and bringing this other CO2 from other customers to the potential gas fields from the Aramis project. So overall, what you see is that the North Sea is, for us and for others, an excellent location for sustainable energy transition developments. On the one hand, for CCS, but even more for the production of green hydrogen. So, and therefore, the further development of wind farms in really gigawatt scales should be brought forward by accelerating, for example, 15 gigawatts, but even much more after 2030. A lot to do, a lot of interesting projects. I'm really looking forward to a bright future on this all interesting energy transition topics. With that, I would like to thank you for your attention. It's a little bit weird to do that in a car and you sitting in this nice room and I'm on the way. It's not the most pleasant form of presenting your project and your company and your ideas, but hopefully I gave you some insight in the developments we do foresee as Gasunie with regard to the energy transition project and also very much in relation to the offshore program. I'm really glad to take any question from your please. Thank you.
Thank you very much, Hans, and definitely also for taking the time on the way. I mean, it's rare that we see presentations coming next from the Autobahn. I don't know if you're in Germany, but and also,
I'm in Germany.
Right, and also a fantastic story, because there is, of course, amazing strategy behind it. The big changes are happening, but also the real investments. The news on the support of the Dutch government for the hydrogen backbone is real news, and it shows the real substance and gaining speed in the transition. Questions from the audience?
Yeah, hello. Is there also a role for blue hydrogen in the backbone?
That's a very good question. Yes, there is. I think as Gasunie, we sometimes say we are kind of colorblind. All the infrastructure we operate via the open access principle and the non-discriminatory principle. So also blue hydrogen could and should be, in our opinion, transported. Probably it will be a transition form because we all aim for green hydrogen, but the access is open for also other colors of hydrogen. For us, the question was also, and we have answered ourselves, is then also gray hydrogen, for example, allowed to be transported? And that's, in our opinion, doubtful, because that doesn't help the energy transition. And we developed this system, and we also got the subsidy granted from the government, this 750 million euros. We got that money for with the aim to accelerate the energy transition. So answer should be gray hydrogen is actually not welcome in this hydrogen backbone. And I understand that is a very delicate topic, but that at this moment in time, this is the position of Gasunie with respect to transporting the different colors of hydrogen.
Right.
Does that, yeah.
Clear policy choices. More questions. Right. Olaf.
Yeah, Olaf Umoev, Flensburg University. I have a question towards the hydrogen islands in the North Sea, which you have in the longer term perspective. And we're talking about 15 gigawatts each approximately, and a number of islands. Now, this morning we have been discussing that we're kind of short of space for all the energy that we need to produce in the North Sea region. How do you see the competition between primary electricity production for direct use and the conversion to hydrogen with the losses along the conversion chain, and the fact that if I transport the electricity from locations closer to shore, my transportation costs are substantially lower. If I have an existing gas pipeline already that reaches out relatively far, I could actually locate the hydrogen islands further out. How do you see the future of the islands if you consider that?
Yes, very good questions. Yeah, indeed, although the North Sea is a big sea, still there are many claims on the usage of the North Sea. So it's not only about energy transition, but also fisheries and other claims are there for North Sea, and rightfully so. I fully understand that. So we should be very efficient in using making use of the North Sea. And that's also the reason why we said, okay, we should concentrate then the energy production and do it in the most efficient way via this energy islands. But it's not only the own production, because I think, and when we look at different scenarios, that it's not about own production in the North Sea, but we do have to import probably also a lot of energy. I've seen many scenario studies. And it's not about, what I said, it's not about the own production of hydrogen in the North Sea. We will probably import hydrogen from, I don't know, but from a lot of places in the world. And when you look also to the energy scenarios of the future, yeah, I fully agree. Where you can electrify directly, you should do that. But many scenarios show that also even in the year 2050, probably about 40, 50, 60% of the energy mix is still molecules. So it's not only electrons, it's still a lot of molecules. And these molecules should be green then. And probably a large part of that green molecule will exist of green hydrogen. Yeah, when you produce that, we as Gasunie, but we do that in close cooperation with TenneT, look at the total energy system. We did this integrated infrastructure study this year, 2030-2050, with many stakeholders. And we approach this study on the basis of the lowest societal cost of maximum societal benefits. And then you see, in our opinion, but not only in our opinion, but also in the opinion of TenneT and many other stakeholders, that probably the further you are away in the North Sea, the better it is to convert offshore the electricity into hydrogen and then bring it onshore. From the perspective of lower societal cost, this seems to be the best solution. Yeah, of course, open for a dialogue on that. That's at least how we see it at this moment in time.
Right, very good. There's also a question, Hans, came in via the chat box. I don't know if you can read it, but it will also be read aloud for the audience here.
I can see it. Okay.
Right, so it's a question from Christian Zuidema from the online chat. He says, based on some preliminary findings of one of the studies that we are doing, there's much more confidence and enthusiasm about hydrogen, notably offshore, visible in actors that traditionally are working with molecules rather than the wind farm developers. Is this something that you recognize as well? And if so, what would that mean?
yeah, I recognize that, partially at least, because that was the what we also heard from many wind farm developers, but it's not, I think it was not the fact that they were against hydrogen, but they had a kind of a fear that by promoting hydrogen too much, that it might block at this moment in time the further development of wind farms, because there was still a need of scaling up electrolysis. There was a need for further development of offshore hydrogen, because that's all new. It's really in the beginning stages. So they were very afraid that when you would couple wind farm development too much and too directly with hydrogen production, then it might block the accelerated development of wind farms. But you see a mind shift in that respect. And just before this meeting, I had another call with the Ministry of Economic Affairs and with one huge wind farm developer. They are really urging for a fast development of offshore hydrogen. And now, yeah, you can either do that directly, integrate it in the wind turbine, or you could do it via a centralized green hydrogen production at the islands. But this big wind farm developer really strongly believes in integrated offshore production in the wind turbines already, and they are really urging the ministry and others to accelerate that development. So you're right, I recognize this original statement, but you see in the meanwhile that there is kind of a mind shift in that.
And another fantastic example that the system change we're looking at really requires collaboration and coordination to align all these efforts. So another question here, please state name and affiliation.
Yeah. I'm Amir Fatay from University of Groningen. I had a question on the prospects of hydrogen import. In your opinion, what will be the main sources of hydrogen import for your network, and how it can be compete with the North Sea source or domestic source inland?
Yeah, of course, hydrogen can be brought and exported and imported via different carriers. So you're talking about ammonia, liquid hydrogen, LCOH. We have done several studies, and not only Gasunie, but we did it together with different parties. Our opinion at this moment in time it's most probable that it will be kick-started with the import of ammonia. And there are many parties and big companies working on this whole value chain of exporting and importing ammonia. And it's going a little bit even faster than we originally thought, because also in my slides I showed you that maybe in the 2030s or later on this really could take off. But in the meanwhile, also Gasunie is already working on an import terminal for ammonia around the 2025. So that's also really picking up. Will this be the end solution, ammonia? I don't know. Could be. And there are also benefits in realizing value chains of liquid H2. Or LCOH, but what I said in the beginning, at this moment in time, when I look to the value chain development, probably it will really kick off with ammonia. At least that's the most projects I see at this moment developing are focusing on ammonia.
Very good, and another perspective added. I think else we could continue talking for another hour, because you have so much to tell and there's so much to ask, but I'm conscious about time, and we're keeping you stuck next to the Autobahn, if that is where, where you are. But we also have a panel discussion scheduled here, so I would like to close the Q&A, and thank you really again for taking the time under those conditions, much appreciated. And I'm sure there will be future contacts with many of the people here in the room. And good luck with the further deployment of the strategy.
Okay, thank you very much, and really looking forward to further dialogue with all of you. Okay.
Okay.
Lots of success.
All right.
Bye-bye.
We are at the last part of our program, Dirk, and we.
That's correct.
Yeah, it feels like the Eurovision Song Contest, right? So
now we're into the awards.
Right. But we have found 4 volunteers, right, to take place in the panel. And one is Annemiek Aschert from EBN. So I think we have, yeah, is that not too far back in the room? We should...
Maybe not, we can move the chairs.
Yeah, I think we should move the chairs. Let's move the chairs. So Annemiek, and then Lars, you already, of course, saw this morning. And then Laura and Xiaoming, 2 of the ENSYSTRA ESRs, want to take part in the panel. And for sure, as distinguished panelists, so thank you for taking place. Lars, is that comfortable for you? You're right. You will for sure get the floor, but we hope that we can gradually move into a debate with the room, kind of Q&A, also maybe evaluating what we've heard during the day, etc., etc. But maybe the first question to all of you that we would like to give you a few minutes, like not an expose or 45 minutes, but a few minutes, to give your perspective on the energy transition in the North Sea. What is the key priority? What is the key problem? What is the key opportunity? Like whatever you want to mention, just briefly, what do you think is the most important in the North Sea? And I want first to give the floor to Annemiek, and also you have some time to introduce yourself.
Yeah. Okay, thank you. Well, thanks for inviting me here. My name is Annemiek Aschert. I work for EBN. This is the Dutch state company for oil and gas, but now I would say energy, because over the last about 50 years we were a participant in all oil and gas fields in the Netherlands. But now we are going through our own transition, like everybody here, I would say. I started my career at EBN exploring for oil and gas in the Dutch part of the North Sea, because we are a Dutch state company, so we only look in the Dutch part. And in the meanwhile, I went through my own energy transition, so to say. Now I'm exploring in another team within EBN for new possibilities for renewable energy. And since we are a state company, always involved in the gas value chain, basically, we really look at the energy transition from a gas value chain perspective, turning it into an energy chain perspective, actually, because, as we've seen today and discussed, it's not just one commodity, but we need to have a mix of all of them. And to get into the role of the North Sea in the energy transition, well, for over 50 years, the North Sea area has played a large role in the energy supply for all the North Sea countries already. And I think we should gradually, of course, transition to a more renewable system, but we shouldn't throw away our old shoes before we have new ones. And as we all heard from Hans Koene as well, molecules will play to have an important role up to 2050. And for now, the molecule demand in natural gas is about 40 BCM in the Netherlands. We still produce a part of that, but the forecast is for 2030 that we still need 30 BCM, that's a billion cubic meters, and we will only produce 7. So it's important to keep producing that, I think, for the coming time, in order to have some economic benefits from that, and geopolitical, not to have too many geopolitical issues. But the most important thing is that producing locally is the most CO2 beneficial option compared to importing gas. But we will abandon a lot of current producing gas fields, and I think we really need to connect the parties involved to be able to use the knowledge that is available, connect the subsurface with the future of the above ground energy transition. And as EBN, we can play a role in there because we have a lot of knowledge of the Dutch subsurface. So yeah, we need to act fast, basically, for the North Sea energy transition to be able to use all this knowledge and infrastructure for the energy transition. So we, for example, hydrogen is of course a main player in making the gas value chain more sustainable. So we are using our knowledge to look into, for example, hydrogen storage in empty gas fields. And we need concrete projects, and might only be necessary of 2030 onwards. But we need to start doing research now, as we are doing, because the TRL is only 3 now, and we need to lift that in order to be able to implement it in 2030. So that's one example where we are working on to diversify our gas value chain business, so to say.
Very good. Okay, that's a clear vision, and also take care of the old shoes. That is also a good one to keep in mind. Maybe Laura first, like, yeah.
So from a spatial planning perspective, I would say that we have to begin with more clear ownership of this transition, and that can happen mainly through, let's say, first of all, organizational, institutional capacity that can better make the links between the important players in this transition, that can therefore take advantage of these opportunities that we have in allocating more efficiently the space offshore. So taking account of multi-use of space or collaboration with oil and gas industries. And this can lead to a more clearer strategic vision of the North Sea, but also a clear view on the main trade-offs that can occur in different alternatives offshore. Of the main losses and gains for different actors that are involved in this transition. And therefore making this transition more just for all the stakeholders involved. And one example of this leadership is, for the Dutch case, the North Sea Agreement that put at the same table the different actors from different sectors. That could come together to a, let's say, a common agreement on how the space can be used in an efficient way for reaching the energy targets.
Okay, also good to hear good examples, but I don't think we have an agreement like that for the entire North Sea, right? It is a national example, so we may have...
But the plea is clear. We don't not just only need energy efficiency, but also spatial efficiency. So perhaps, Lars, you can also...
Well, I thought about what is important, and a lot of things are important. But, and I think we are in lack of time, in fact. And every huge project, it takes time. And the authorization processes are very complicated and time-consuming. So I think it is necessary to achieve simpler or at least higher tempo in the authorization processes. Of course, it is difficult because there is a lot of things to take care of. It's a natural environment and so on, and space. But even it is a lot of things to take care of. We must get a more rapid process for the authorization, I think, to achieve the goals we are looking for. And then we have the market solutions, as I mentioned earlier. It is necessary to find solutions to pay those who need to be paid. New projects especially in regulating the system and compensating for variable renewables, we must have systems that will pay for the investments and operations, but mostly for the investments, because that is not paid by the hourly price, so as the market is. So we have to find a way to solve that. And then it's also a huge problem when I look to Norway, and we discussed a bit in the lunch. It is Norwegian public, they are happy to have low prices, electricity prices, very low electricity prices. And now, when we are connected better to the continent and to UK, the prices have been multiple higher. So that is a political problem. So I think it's impossible, in fact, for the politicians to accept a lot of new connections and a lot of new projects without solving that price problem. And solving that, I think, will be quite difficult, but it has to be done. Otherwise, we will not develop these possibilities at all. And it is for the common consumers and also for the metallurgical industry. I think those problems is crucial.
Very good. Both the planning and the realization procedures, and then also how is the market organized. Those are, I sent some messages to governments, but okay, Xiaoming.
Okay, hello again everyone. I'm ESR3 from Chalmers University. So I'm a modeler. So I want to talk something starting from modeling results. So as you see today from our results, we have certain amount or certain share of wind and solar for the future electricity system for the North Sea. And I want to ask you one question. Why there is such amount of wind and solar in the system? Why not nuclear? Why not fossil?
The panel asked questions to the audience. That's interesting. So shout, shout.
That's a very provoking question also. Okay, so let me answer my own self question. So we always say models are wrong, but some are useful. So what is the wrong part? Sometimes you made some assumptions. People say your assumptions are wrong. So why we have so much wind and solar in the system? Because we have a cost assumption where wind and solar is relatively cost competitive. So why wind and solar become so cost competitive? Because there is support. I think 50 years ago in the report, Limit of Growth, the future is about nuclear. And 20 years ago, you wouldn't expect solar can be as cheap as nowadays cost. If you look at the past 10 years, how much cost reduction for solar? Because there is policy support. And this starts from Germany's energy transition. This because of the feed-in tariff, because of the green certificate. And this is a very, very good example how the policy in the North Sea region and also the measures taken here can help to deal with energy transition. And this example has been followed by many countries in all the world, in China, in every corner of the world. Countries support renewable energy with feed-in tariff, with other policy mechanisms. So this is a successful example. And also we today talked about the political barriers to handle this sharing of Nordic hydropower. I'm sure we have measures to overcome this barrier with better communication, with better price signal, with the urgency of climate change problem. So I think what is very important here with the North Sea region is a pioneering area with very strong ambition. We see this hydrogen project, so it is already ongoing, it is being planned. So it might be not the best, not the efficient, but this is a starting point, sending the signal to all the rest of the world, you can make a change. I think this is something, a very strong point from the North Sea region. We might have some, problems with collaboration, with national, with the collaboration between different countries, collaboration between sectors. But we have a common enemy, that is climate change. I think with that in mind, with very strong willing to handle that, we will achieve this target of energy transition in the North Sea, and then spread the example to all over the world. So that's my part.
Much appreciated, and it's a very good point, because the support given has a major influence on the speed of development and deployment. So that is, in that sense, the models do not predict.
It really sounds like a Eurovision as well. So that's
very
good. Yeah.
Right. I would propose, Dirk, that we move to the audience.
Yeah. So who has a question for our panel? Oh, there's already one volunteer.
So there's something I worry about a little bit. So I think in Western Europe, around the North Sea, there is, among the general population, a general support for the energy transition, not universal, but general. But consumers haven't really been asked to do anything yet. They haven't had to change their behavior. Prices have gone up a bit, but not that much. That's changing probably right now, with carbon prices at 65 euros and gas prices going up, government starting to spend significant amount of money, which comes from taxpayers. How do we stop, at some point, that process of consumers having to change their behavior and having to pay a lot more from just, cancelling the whole thing, which I feel is a danger.
Interesting. Who from the panel would like to respond to that?
I can give it a try. Yeah, I think this is one of the most difficult issues of the energy transition, because we have all kinds of technical issues which we will overcome, I think. But the societal change and keep it payable for everyone is the major challenge, I think. So I think if I focus on the Netherlands now, for example, I think the government has a role to play there, and I think the government needs to have a stronger vision on that and how to solve that problem, because now, yeah, the government is not strong enough on that point, I think. So it's that's not a total solution, but I think the government has a role to play there to keep the energy transition for everyone reachable.
Yeah, sorry.
I want to add some point here. So maybe 10 years or 15 years ago, when electric car is first in the market, people might be like curious. Okay, this is a new toy for the rich people. But majority are a bit hesitant because they are worried about, okay, where can I charge it? Where is the infrastructure to support the car being used in the general society? So this somehow point out, sometimes you have something which is good, which is energy efficient, but you have a gap there for the purpose and also the potential consumers, how much they'll use it. So the point is you need to provide extra infrastructure to make the use or the adoption of the new technology more convenient. So this is, hand in hand, not only one way, but you need to do it on both sides of the coin. So that's my point.
Very good. More responses? Lars? Yeah.
When it comes to the transportation, as you probably know, in Norway, it has been much cheaper to use an electric vehicle. And now, last period, I think more than 70% of all small cars that was sold was electricity cars. So it is a question of a price. That's an important part. And as the time rolls further and the production lines are greater volumes, prices general will go down. So I think for ordinary personal cars, it will be solved by the price reduction. But then we have heavier transport, and both for small cars and even much more for heavy transport, the batteries are heavy. And as told here about biofuels use, he calculated with the heavy batteries we have today. But I think there will be technical development in battery technology. Many probabilities are there. And when we can develop batteries with the same capacity and half of the weight, that will revolution some of the transport. So that's one example. I think many things can be changed through technology development on different fields in the coming decades. And I think we should also be aware of that.
So basically you're saying we need a mixture, but it's also basically what you're saying, right? We need government, but we also need to have higher TRL levels. So
there is an issue now that there's already, I was reading this morning actually, 500,000 households or so in the Netherlands that have energy poverty, and especially with the prices rising now, there's already quite an issue, at least for those people, and those will be the most hesitant, I think, to fully step into the energy transition. So we need to find a solution for that.
Society is diverse. Laura, you want to respond?
So as Annemiek was pointing out, the energy transition will come with clear costs on both the industry, society, and those costs need to be covered maybe partially by the government, maybe through subsidies, but also through identifying which are the categories at risk, as you were mentioning, the households who are not able to pay the rising energy costs. I also believe that there can be different measures that can be taken to overcome this. For example, energy efficiency through making houses more energy efficient, or taking policy measures that support this process. But nevertheless, this energy justice should be a topic that should be addressed as part of the energy transition.
Absolutely. Just in between, I would, if the people in cyberspace are watching and say, I want to ask a question to the panel, please do so via the chat box, and your question can be hoovered here into the room. So
yeah, we have technology for that, so that shouldn't be the problem. In the meantime, perhaps also some questions from the audience here. Are there still some, perhaps? Ooh, I hope it's provocative.
I think
no
that
pressure.
will not be the problem.
Well, no, just one observation. If we're talking about, as Harry said, well, changes in cost to consumers, there's one thing we might not forget. Costs are driven up partially because CO2 prices are increasing. But where's the CO2 money going? It can be redistributed. And if we combine that with the last suggestion, that we look at the groups at risk, then we have a lot of money to actually levelize that. And that's one of the ideas behind the German redistribution scheme, that the money that's taken in through the CO2 levy is redistributed. So energy, clean energy, does not become that expensive. And it's prioritized. If you go for gray energy, it's expensive. If you go for green energy, it's less in cost. And the other thing that we see, and it has been mentioned a couple of times, is we see these learning curves and the cost going down. So if we combine that, we may get into a situation where it's still possible to reconcile, the growing costs on one side and the consumers not being exposed to too much. And what I would see is not the cost aspect. makes it difficult for consumers. If we get to a point where we say you need to change your lifestyle, and then we're not actually targeting the low-income groups, we're targeting the upper middle income and higher. Those guys with the SUVs, they have the biggest problems changing their lifestyles and their emissions. And how would you deal with this very influential group of people saying, you can do everything, but don't take my car away, and it has to be 2.5 tons?
That's the same income group as the ESRs that are going to get great jobs after the PhDs.
So who does own a SUV in this scenario?
But it's a great question, and also point, like, are the costs really the problem? Because we have these balancing mechanisms, and on top of that, we have capital in surplus with negative interest rate. So our cost the problem? Is the problem somewhere else? Maybe that's a nice question for the panel.
Splendid question, I'd say.
Who would like to respond to that? Olaf's sketch, but maybe also indeed, are we focusing too much on cost?
I think a lot of those people you are referring to are actually working on the energy transition. So there's a role for us, I think, to spread the word. But I think we also need to diversify the people who are actually working on it, because now it's generally led by one type of person. And I think if we diversify the workforce working on the energy transition, that might help, well, I would say tremendously to get the words out and change behavior, because then you lead by example and then have similar people who are actually doing that and giving an example of how we can adapt the energy transition in our daily lives.
Good observation. I think if everyone would be as diverse as this panel, I think the problem would be solved. Although, yeah, Lars, I mean, you look much younger than you are actually, so that's might be a bit deceptive. But who would like to respond to that? Maybe Lars. It's a nice one for you.
I can say a little more about the problem in Norway, because we had an election now, and the parties that were winning the election, they are to the left and middle, and they are very much influenced by trade unions, for instance. And it's difficult, I think close to impossible for them to hire the prices on electricity for the industry. It's they can't do it politically, so it is not easy. And as I said, in a way, we must find a way to probably give them lower prices in the future also across market signals, if we shall be able to realize further connections and develop the flexibility resources we really can.
Okay, maybe also Leire, Xiaoming, you want to respond to the cost issue, and are there other things that should be prioritized? Xiaoming?
I think this question reminds me of one comment when I have my master's study back in Italy. So the professor asked us, so, okay, you can change your lifestyle, change to, more energy efficient way for cooking, for everyday use. But what about barbecue? You still want to use charcoal. So this is a very, very, tricky question, because sometimes people are locked into certain way for life, for the utility. And nowadays we are very, very relying on electricity for almost everything. So I think this is one part. But on the other hand, as a part of the course, I have 140 students now. When we do the debate, when I talk with students, they are also willing to make a change, to consume less, to say, okay, we can sacrifice a little bit. So to help with this problem, so I also see hope in this sense. People are willing to change. So I think I don't have a absolute answer to this, or is there any way to solve this problem? Of course, the communication, the influence of education, of course, it matters. And also, I think, as we mentioned about these, equity problems, so don't leave anyone behind. If you have energy transition, it shouldn't be at the cost of fairness. So people should still be able to, access affordable electricity. So I think it's something hard to balance, but something one has to balance. So I think if the North Sea region can really have some good experience in the future and spread to the world, I think that'd be a great treasure. Yeah.
Very good. Laura, you want to respond or?
So I have to agree with Xiaoming. I think it's a lot about education and awareness in a way. So in this regard, I think as researchers, we have a very big role to play in that, in spreading, let's say, the word and making our results more visible and raising awareness. And when it comes to changing behavior and customer behavior, I think that a big role is played by the options that we have as customers. So maybe it's also our behavior that needs to be changed, but also what options we have in the sense of more sustainable options, how affordable they are. So it can be also a mix of the two, the awareness that we have, but also the options that we can have on the market, let's say, as consumers.
Sounds fair. Perhaps some responses from the audience or some questions.
More questions, other points, other observations.
Observations are also welcome.
Right. I think.
I see. Is it an observation or a question? Okay, good. Yeah.
It actually is a follow-up question to Lars. You said we have this problem with the access to the fantastic Norwegian resource for storage, that the cables that we create, the connections that we create, give price signals into the Norwegian electricity market, which then lead to the fact that the consumers and the industry says no, because our prices go up. Now, it struck me that if it would be possible to separate those markets and say, okay, we have an internal market which does not interlink with the external exchanges, and we have dedicated exchanges for storage, which have their own pricing. That would certainly require a large demand for storage to keep those power lines busy and to make enough money on the power lines, but it would allow to kind of put a firewall in between the two pricing systems. Would that help to actually keep the Norwegians calm, say, okay, fine, if this does not impact on us, we don't care if you're selling your capacity, and if you're better off due to the seasonality that corresponds between the wind and the hydropower system, the hydropower operators are better off doing that, but it does not intervene into the Norwegian internal pricing mechanism. I know this is very difficult with Nord Pool and all the mechanisms that you have in place, but it just struck me, could that be an option to actually tap into this resource?
I think that is an interesting question, but I'm more thinking maybe about Harry and the ESRs that are working and have been working on the markets and the mechanisms and all that. Harry, or maybe some of the ESRs are online that have been looking at these issues. That's, I'm not sure about that.
I think that's actually a good suggestion.
Right. Well, Harry, would you, I'm tempted to ask you to respond to Olaf's point.
Yeah, so for me, I don't really see the big challenge here. I think there's an easy solution, which is in the case of Norway interconnection, let Norway capture the congestion rent and use that to redistribute that money to keep consumers in Norway happy. So make sure Norway owns the interconnector is, I think, part of the answer and make sure that that money gets redistributed within the country. So I think these are things that we can solve within existing structures. We don't even need new ones. We just need to make sure that ownership structures are correct for cross-border infrastructure projects. But maybe there are other people who want to comment.
I think we can give the panel one last round of response, and then we have to head to the closing statement of André.
I don't have the answer how to take care of the problem we have discussed about Norwegian industry and also Norwegian consumers. But in fact, I think it is necessary to be solved in a way. What Olaf proposed, in fact, in a way has been tested, but not accepted by the authorities in Norway. It was a project a long time ago, and building connections directly to special resources in Norway, and without connecting to the internal market. But it was not accepted by the authorities. And I think the reason there was many other companies that will not earn on this disagree and influence the decision. But I don't know, as I said, but I think theoretically it should be possible to find a solution. But then if we find a solution on the paper, it is a question, will it be accepted for the EU regulations authorities, for instance?
Okay, thank you. So other panel members, final statement, you're free.
Okay, so I want to add one point for this question. So I want to remind you of the function of transmission grids. So transmission grids or electricity trade, on the one hand, it can share the resource for variable renewables. And on the other hand, it can also share variation management strategies, such as the storage for hydropower. So when we are talking about this question, we are talking about Europe is benefiting from Norway, so it's like a one-sided thing. But what if there is continuous drying for many years? Well, in that case, Norway also benefited from the continental Europe. So this year, early this year, we see the case in Texas. So we see the problem there, and it has very bad consequence. So in that case, remind us, interconnected transmission grids or interconnected system can help to maintain the resilience of the system. You don't have to black out if you have good connection because you can borrow from your neighbors. So I think this question, it's not only about Norway or about the European continent. I think it should be a win-win case. So I think there should be the way to communicate well, to have a common benefits or share the benefits from both sides. So that's my point.
Just a comment. Of course, it is a benefit to secure the supply in dry years. But I think the existing connections already is enough to cover that. What we talk about is much higher connections and regulation installations.
Not on this topic, but in general, I think in order to speed up the energy transition, we should focus, of course, on the technical part, but also on the cooperation between, well, so to say, the old energy companies and the new energy companies, because I think there's a lot to gain there to speed up the energy transition. So cooperation and connection and be kind to each other will help.
Yeah, let's talk to each other. Good. Yeah, that's. I think that's a very good closing statement. Or do you have a better one, Laura? Feel free. You may.
I believe that this answer has been already very well answered. This question has been already well answered. Just to sum up, I think maybe it is about trade-offs, so making it very clear which are the benefits and risks of all the options that we have on the table, and having a clear vision on how to move forward.
I think that closes the circle, right?
Absolutely.
And now I think we can thank our panel for their nice input, the good discussion. Thank you for that. I think we had a bit shorter than anticipated discussion, but nonetheless a very good one. We had some provoking statements and questions, so that was good. Of the day, so I think, Andre, it's up to you now.
Sure. First, an applause for the panel. So,
yeah.
Okay, you can take your seat. Otherwise, you're kind of in a limbo situation. And don't be afraid. I'm now not going to take out my 300 favorite PowerPoint slides and stand in between you and the drink, which is probably the most important part of the day. You're physically here. You're physically here. Congratulations. So this is also victory over COVID. You were brave enough to come, and the drinks are, I think, the biggest symbol of that we're going gradually back to normal life. So that's good. But also to everybody who's still online. There are still people online? Oh. So thank you for your attention, for joining in. It is after 1.5 or more time being online and in the two-dimensional world, it's even more laudable that you follow this event from a screen, but that's great, and I hope it was interesting for you. But some closing words. I think the panel, the content that you have seen today make clear how much is going on, how much is happening, how much insight has been gained, how much we know, how much is invested, how much is built. That's fantastic, but also how incredibly much we still have ahead of us. So although the models are incredibly impressive, the policy analysis give great insight. We know a lot about the technologies. The discussions we have show there is more to do. How do we accelerate the implementation? How do we organize those markets? How do we do the innovation faster so that the costs reduce? And how do we share the cost in a fair way? Just a few points. And then balancing the energy transition with many other priorities: environmental, space, social, biodiversity, resources, the metals and all else to come from there. So there is so much more to do. And that's great because you have been trained as top researchers. I'm now talking to the ESRs specifically, the ones here and the ones online. Because let's not forget, final conference of the ENSYSTRA project. It's a kind of also melancholic moment, but the key objective, of course we did great work on the North Sea energy transition, but the key objective, it's a training network. It's a Marie Curie training network. And the key product, oh, what a terrible word, the key product of the project is trained researchers, highly skilled researchers. And the original plan, the original proposal, that was so good because we won it. And Sandra, I want to mention you because in the back of the room, Sandra Dijkstra is one of the people who was vital in making the quality of that proposal so high that we got it approved. So that's really an achievement. But the key objectives listed there were indeed about the skills of the researchers, interdisciplinary skills, the ability to work with multiple disciplines, the ability also to integrate those results, understand them, and work in very different environments. The secondment partners, all the companies, the government bodies, the research organizations that have contributed to it, and some of them may still be listening, were also an essential part and have contributed an essential part. And I think those experiences in that Marie Curie training network, including the summer schools, although unfortunately a large part of them were online, did provide a unique opportunity to get those skills. I can tell you, ESRs here and ESRs online, you are extremely precious. You are extremely important for the challenges and the transition that we have ahead in the coming 3 decades and probably beyond. That is why you were selected. That's why you're doing the research. And that's why I think you will be extremely welcome in the labor market, wherever that will be. So that is, I think, the biggest achievement of the Marie Curie training network. And that's your work. I know some of the theses are not finished, for sure. There's a lot of hard work to do. But I think we will have 100% score from the 15 positions that were started. And that is, of course, also due to the hard work of all the supervisors everywhere, the help of the secondment partners, and also very good management. So an applause for all of you. And from my side, I can say it was a pleasure and privilege to work with all of you. It sounds like a goodbye, and that is in a way true for the closing of the project. So administratively, I hardly dare to look at Dirk because he is the one who really dealt with the tough issues on the... Right. You're simply, you're a unique guy that you know how to do it, and you're good at it. So I really appreciate that. Without you, it wouldn't have run this way. So there will be some closing things. And of course, I think even the majority of the PhD thesis still needs to be defended. So you will see more papers coming, more tools coming, more defenses coming. So by all means, report that and let us know. Let's keep that network together, because I think the context that you got over time, despite the online intervention of a pandemic, will be precious for the rest of your career. So I will be very happy, and I think I speak on behalf of the entire coordination team, be very happy to stay in touch with you and also stay learning where you end up, what you will contribute, and maybe also collaborate in the future. So that's, I think, what we have done with ENSYSTRA. What else to say? What else to say? Yeah, the final event. Yeah, I think I've basically said it all. The final thing I want to say is a big thank you for the organization, Deborah. You have really worked very, very hard. Changing it from a physical event to an online event to a hybrid event or whatever, but it worked out, so well done. And I think you should now all get drinks. Right, I was thinking about a different word. So go ahead, have fun.